optical communication, microelectronic system, electromagnetic and electronic materials, emerging and advanced fabrication technology, and so on. JET is indexed by internationally renowned indexers such as the OAJ, Google Scholar, Mendeley, and etc. JET is also ranked as Center 2 in Kemendik's BRIN accreditation system. There are 2 JET editions published every year, and all of them are available in open access to support global exchange of knowledge. All submissions in JET are accepted online, and each submission will be blindly reviewed by at least 2 peer reviewers. Most importantly, all submissions are free of charge, and therefore, no article processing fee applies. For more info, please visit www.journalet.com or visit our social media accounts.
Research is our strength to overcome any limitations. Innovation is the guiding vision that drives us towards the future. We cannot face this alone. We must stand together to make our vision a reality. Growing strong upon the land of Nusantara, a magical place filled with miracle and wonder. A land spanning 2 continents and 2 oceans, rich in culture and biodiversity. We and Indonesia are the necessary combination to realize the grand visions of the future. Like an orchestra, BRIN harmonizes research, development, assessment, application, and also synergies, invention, and innovation in Indonesia. We created an ecosystem consisting of 7 deputies, 12 research organizations, and 85 research centers dispersed throughout Indonesia. Research Organization for Aeronautics and Space, Research Organization for Nuclear Energy, Research Organization for Energy and Manufacture, Research Organization for Earth Sciences and Maritime, Research Organization for Life Sciences and Environment, Research Organization for Electronics and Informatics, Research Organization for Social Sciences and Humanities, Research Organization for Archaeology, Language, and Literature, Research Organization for Health, Research Organization for Nanotechnology and Material, Research Organization for Agriculture and Food, Research Organization for Governance, Economy, and Community Welfare. BRIN catalyzing research and innovation to develop an advanced scientific ecosystem in Indonesia with 2 main targets. BRIN realizes the tremendous potential of the nation's youth in the field of science and technology. Thus, various research and innovation policies are being formulated to develop and cultivate human resources with high competence and aptitude in science and technology. Creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized
Recording in
through
progress.
the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or RIDA. Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums. BRIN organizes research into a more effective and efficient process by integrating human resources, infrastructure, and budget from various research and development institutions. Oriented by a national research priority, BRIN routinely enacts comprehensive evaluations from various research and development institutions. This effort is supported through the continued management and improvement of various research and innovation facilities located across 17 regions of Indonesia, dedicated towards the development of science and technology. BRIN continues to improve our contribution to research and innovation towards national development by developing and revitalizing 4 areas of science and technology, or KST. An integrated area consisting of research laboratory facilities, testing laboratories, and industrial facilities for both startups and SMEs. Tenant office rooms, co-working space, meeting rooms, gallery rooms, and other supporting facilities. BRIN is here to manifest the future of a golden Indonesia 2045 by consolidating science and technology resources and creating a resource ecosystem and research-based economical foundation. Transforming Indonesia as a global reference in the development and
How can you design the perfect car before driving a single mile? How do you construct a building that redefines a city before building anything yourself? How can you develop world-changing tech without changing your timeline? The answer is simulation. Physics-based simulation generates insights at every step of product development, allowing your creations to get certified, compliant, and on the market sooner. This means you can build a virtual cruise ship and see how it fares on the open sea. Erect a full-scale virtual twin of a factory and make certain it will be operational in real life. Construct the ideal commercial aircraft and ensure it can withstand the elements. With simulation, no matter what you dream up, it will be enhanced with data, insight, and most of all, revelation. Simulia, reveal the world we live in.
Welcome to the second day of the 2024 International Conference on Radar, Antenna, Microwave, Electronics, and Telecommunications, or ICRAME 2024, with the theme of Accelerating Digital Transformation, Cultivating Electronics and Telecommunication as Open and Innovative Technologies for a Sustainable Future. Today, we will have 2 keynote talks and 8 paper presentation sessions. For the first agenda, we will hear a keynote talk by Professor Yoshiki Yamaguchi from University of Tsukuba, Japan, followed up by the parallel sessions. There are 3 breakout rooms for the morning session. Parallel session 7 in breakout room 1, session 8 in breakout room 2, and session 9 in breakout room 3. And after a short morning break, the agenda will continue for the 3 breakout rooms for parallel sessions 10, 11, and 12 at 10:40 a.m. GMT+7. And after the lunch break, there will be only 2 breakout rooms for parallel session 13 and parallel session 14 at 1 p.m. GMT+7. And after we complete all the parallel sessions, we will hear the 4th keynote talk by Associate Professor Jia Feng Yao from Nanjing University of Aeronautics and Astronautics, China. Also, I would like to encourage all of you to please stay tuned until the end of the conference. We will have the award announcements for the best paper and best presentations will be awarded by the Technical Program Committee before the closing of ICRAME 2024. I also want to express our gratitude again towards our patrons, PT Radar Telekomunikasi Indonesia, PT Nusantara Sekom Infotech, PT Mars Sistem Integrasi, PT Serviam Abadi Murni, PT Young Dinamis Indonesia, PT WAP Andalan Indonesia, Bank Rakyat Indonesia, and PT Land Railway System. Thank you so much for your support for ICRAME 2024. And let us begin our second day of ICRAME 2024 by inviting all of you to participate in a screen capturing session. I would like to request all honorable guests, distinguished speakers, presenters, and all of the participants to turn on your cameras. We will capture the frame 3 times, and I hope by now that all of you already have the virtual background of ICRAME 2024 as your background. So I will wait for around 10 seconds probably to allow you to get ready. Okay, please turn on your camera. We'll start in 5 seconds. Okay, for the first screen capturing, I will count in 3, 2, 1. Thank you. And for the second, in 3, 2, 1. Okay, and for the last one, in 3, 2, 1. Thank you for all your assistance in the screen capturing session. Okay. So now we move on to our first agenda for today. The first keynote talk of the day will be delivered by Professor Yoshiki Yamaguchi from University of Tsukuba, Japan. I hope that Professor Yoshiki is already with us this morning. This session will be moderated by Dr. Iman Firmansyah. First, I would like to introduce to all of you Dr. Iman Firmansyah. He received his Bachelor in Physics from Universitas Padjadjaran, Indonesia in 2004, and he holds 2 Masters, first in Physics from Universitas Indonesia, and the second Masters from Chiba University in Master of Engineering. In the University of Tsukuba, he receives both his PhD in Computer Science and continuing the postdoctoral position, also the same university, University of Tsukuba. He joined Indonesian Institute of Science, or known as LIPI, since 2005. And currently, he joins the Communications and Signal Processing Research Group under the Research Center for Telecommunications of Indonesia's National Research and Innovation Agency, or BRIN. Dr. Iman Firmansyah's current research interest is signal and image processing using field programmable gate array or FPGA, also embedded systems and IoT. Please welcome Dr. Iman Firmansyah and Professor Yoshiki Yamaguchi.
Okay, thank you very much, MC, for introducing me. By the way, can you hear my voice? Is it okay?
Yes, very clear.
Okay, 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 thank you very much. Okay, good morning, everyone. So, welcome again to the second day of the 2024 International Conference on Radar, Antenna, Microwave, Electronic, and Telecommunication, or ICRAMET. Today with me, my name is Iman. So this conference, the title for this year is Accelerating Digital Transformation, Cultivating Electronics and Telecommunication as Open and Innovative Technologies for a Sustainable Future. Okay, so once again, thank you for all participants and speakers for being here with us today. So this morning, it is my pleasure to introduce our next distinguished speaker, Professor Yoshiki Yamaguchi. Ohayou gozaimasu, Sensei. Are you there with me?
Yes. Can you hear me?
Okay. Great,
Okay.
Sensei. I can hear you.
Yeah. Yeah, thank you very much.
Okay.
So thank you for introduction.
Okay. Professor Yoshiki Yamaguchi will be sharing insightful topic related to FPGA or field programmable gate array implementation. So what FPGA is and how FPGA can be implemented for, we will hear from Professor Yamaguchi later. But before we get started this interesting presentation, please allow me to introduce who Professor Yamaguchi is. Okay, MC, could you please show the biography of... Okay, so Professor Yoshiki Yamaguchi graduated from bachelor degree from University of Tsukuba in 1998, and then he continued to get master and PhD from the same university in University of Tsukuba, Japan. And then currently, Professor Yoshiki Yamaguchi not only a professor in University of Tsukuba, he is also a professor in Kumamoto University in Japan. Okay, and then his research interests include architecture for high-efficient computing system and constructing high-performance computing system. Okay, in this session, the presentation will be limited to 30 until 35 minutes, and then the session for Q&A is about 10 minutes. So for all participants, if you have any question, please do not hesitate to raise your hand, or you can type question or chat book. I will read them for you later on. Well, anyway, without any further ado, this morning, Professor Yoshiki Yamaguchi will be discussing the topic. The title is Unlocking the Potential of FPGA, Exploring Evolution, Diversity, and Future Direction. And we are so excited to hear his perspective on this important topic, I believe. So, Professor Yamaguchi, please share your insight with us.
Yeah, okay. So thank you very much. Thank you for your introduction. And can I share my screen?
Okay, please.
Can you see my shared screen?
Not yet.
Not yet.
Okay, it's work now. Go ahead.
And also, can you see my pointer, laser pointer?
Yes,
Okay.
it can be clearly. Okay, it's perfect.
Okay, yeah, so thank you very much. And yeah, thank you very much again for providing me with this valuable opportunity today. My name is Yoshiki Yamaguchi from the University of Tsukuba. And I have been conducting research using FPGA and around 25 years. FPGA is one of reconfigurable electric device and unique and interesting for me. So today I would like to reflect on my experience and discuss the potential of FPGA. First, I want to give a brief introduction of FPGA. Probably you may know, but please check and see this slide. So FPGA stands for Field Programmable Gate Array. The term field programmable. Yes, this means that its configuration can be reprogrammable on the site. And while gate array refer to the grid-like structure, yes, here. So it complies as shown in the diagram on the this. And the FPGA is composed also 4 primary elements to enable various computation. CLB, switch box, and channel and IOB. The first component of CLB, yes, in this slide, you can see the 16 dark boxes. And CLB performs the operation based on function set by the user. This part varies depend on the FPGA and may include small memories. Sometimes we say lookup table, or arithmetic unit. That difference influences the suitable application for each type. The next section calls routing logic, like switching box and channels. Sometimes we say interconnect. This interconnect connects each this CLBs. Well, for example, this one and this one, and this one and this one. And it means this wiring programmable, allowing designer to configure the data flow needed. And IO block, input to output block, yes, serves as a port to facilitate signal exchange between FPGA internal circuit and external devices like sensors and in this time, for example, microphone and headphone and something. And IOB enables the FPGA to interface with external device such sensors and actuators. Wait. So now that I introduced some of the characteristics of FPGAs, and I want to ask, what kind of image do you have of FPGAs? And here, first, let me introduce a supercomputer that the University of Tsukuba currently owns. This signal supercomputer includes many FPGAs. This project was led by, not me, Professor Boku, other professor. He is also my boss, and University of Tsukuba. This system consists of 2 types of accelerator devices. One is GPU, yes, this one, GPU, and the second one is FPGA. It means we can say this is a heterogeneous supercomputer. This system is also used in many applications, such as radiation transfer simulation, and also weather simulation. Sometimes tsunami or earthquakes, and some scientific simulations. But for me, from an information engineering perspective. It was developed as a system to verify, implement in the power consumption to performance ratio in scientific computing, and also to optimize network communication. Not only high performance computing, but also, sorry, I don't know, but maybe don't do, but anyway, I also implemented various application over the years. Initially, I focus on the application in bioinformatics. The developed system uses multi-large-scale FPGA, but recently, at that time, I belonging to the RIKEN, the National Institute, but now in the university, and the university has not great fund, therefore, currently, I developed many embedded systems, especially collaborating with, for example, this one, car company, motor companies. And this one is photo shows developing autonomous driving in my mind. And in the experiment, FPGA platform, communication, processing in real time to enhance the reliability of ad hoc communication between vehicle traveling in a convoy. And FPGA board is here and here, and communicating between these two golf cart. And sending video images. Here is the video camera, and capturing data and sending to the following car. And the following car analyze that image, and if they found emergency was terrible accident at the time, automatically stop before human understand. And this one is the camera system. We use not only the CMOS, general CMOS sensor, but also the TOF, time of flight sensor. This is the FPGA based time of flight sensor. And therefore, we implemented some point cloud processing on FPGA. And also, this is TOF, time of flight sensor. So we can capture the image in the low light conditions, or no light conditions. Then we can mean the car with this camera can drive the very dark situations with no camera. And also drone, and this motion history capturing is I will explain later. And other is for example, immersive display. And okay, and currently we are also developing immersive display, and this is developing for the remote control for this kind of the remote vehicles. And then, I would like to say and introduce, probably you can understand the FPGA can adapting to the high performance computing and also the embedded computing. But for me, especially I am reconcilable hardware or so architecture researcher, and we need to find the killer application for FPGA. So many people, so many FPGA researchers, so would like to find the good killer application. Therefore, many application was implemented on FPGA. So it's so very difficult to classify the such kind of application. Therefore, I would like to start FPGA vendor classification and FPGA architecture classification. And this is FPGA the transition, and now we have maybe microchip, and Intel is acquired Altera is a very famous company in FPGA field, and AMD is also acquired Xilinx company, and Lattice and ST Micro. And I think these Intel, AMD, Lattice, and Microchip, these 4 companies is the top 4 company in FPGA industry and FPGA market. So yeah, this is the sales trend of the FPGA market. And these 4 companies, sales is almost 98 to 90% of FPGA market. Therefore, if we analyze this, then we can understand the trend of FPGA market sales. And this figure shows from 2002 and from 2021, FPGA sales trend is increasing. Some years decreasing, but almost we can say that FPGA market is growing year by year. But yeah, I added this purple birds. What is purple bird? Can you imagine that? Yeah, so this is a GPU, and this is GPU, and especially 2016 and 2017 here has a very big gap. And this is one article, and around 2017, computational performance is over the human's ability. This article says, but this is very interesting because GPU, especially only one company, NVIDIA's sales is overcomes also FPGA market. So before 2017, GPU and NVIDIA and all FPGA market is equivalent. However, after 2017, we have a big difference. This is very important, but I think. And I like to add some and industry informations. Probably Microsoft investment is OpenAI, and in January 2023, Microsoft announced around 10 billion investment in OpenAI. This is one article, but OpenAI directly says the AI system requires a huge amount of the money. This last one says OpenAI financial portion and investment, and OpenAI is projected to record a loss of about $5 billion in 2024, primarily due to expense of roughly $4 billion for ChatGPT system operations and $3 billion for AI model training. This is too huge. Their AI, this kind of AI companies need to collect big money and also pay and continue to develop their own systems. Therefore, so yeah, I think so. This is one reason of NVIDIA's growth. But so FPGA is yeah maybe so miss direction this, and so is there room for FPGA adoption? So AI models are becoming so more sophisticated, and the computation demand is increasing. Especially so parameter topes and layer is so increasing by so increasing. So the number of parameters is increasing. So therefore, yeah, some people say so FPGA has a programmability and so recoverability. However, model is not fixed. The development cost is too huge for FPGA. Therefore, so in this moment, FPGA is not the killer device for AI, especially so AI learning systems. But now the so some embedded AI systems, so AIoT devices, yeah, so FPGA can be used because so model was well studied, and so we can use some so fixed AI models. And then so yeah, I will to continue the introduction of FPGA devices. This is so FPGA device evolution. But please note that so the horizontal direction is so lookup tables, and so vertical direction is digital signal processing, so DSP units. We say DSP units, but this is so arithmetic unit. Not by so ear, by so circuit, both are so circuit. But this is so very, I think so good measure for good index for FPGA. And if we see, and so we classify this in the, so I think so FPGA can be classified into 4 groups. Yeah, well, first group is so group logic and so sensing. Yeah, this one. And the next group is so SoC FPGA. And the third group is so rapid prototyping and specialized computing. And the last one is so high performance and large scale computing. So we can, yes. And first, so I would like to explain and so show the this group, tiny or so small system, so group logic and so sensing. This is yeah, directly says so very traditional so FPGA group. And yeah, but so I think that this has a so FPGA potential because so very small, tiny and so small devices, but good power performance devices. And so in our yeah, so in our project, currently, so we are focusing so inspection system, especially for the so skyscraper, so very tall buildings, because so for water resource management and heat resource management, Middle East and so African countries so introduced to build the so very high buildings, so namely so skyscrapers. But the construction fee is so very huge. Therefore, so they need to maintain and use this building more than so 100 years. So it means so we need to maintain so these buildings for a long time. But some people say that so yeah, use human do that, but more than so 1,000 layers and some places so very dangerous. Therefore, so only human inspection is so not reasonable. And so some people would like to introduce drones. However, many people think that drone, but that drone size is more than 1 kilogram. So if the drone, for example, attack the small child or baby or sometimes hit the walls, and then probably it will be a big problem. Therefore, we propose a small micro drone device like this. And this drone is too small, around 30 grams, 27 gram drone. However, the battery is too small. Therefore, the flight time is currently is around 7 minutes. Therefore, こっちなのか。Yeah, therefore, the power consumption of information system related to the weight is not negligible. Therefore, the currently preliminary investigating using FPGA has begun for us, our project. Andあれスライドショーだけど、ちょっとplease wait。ちょっと共有を停止して、これはこう、これ、これが登場される。そしたら、これで、動画をYeah, this is my micro drone project, and left one is color detection, and this drone detected the color on the floor. すぐ止まるな。それ。And if green, this drone goes straight, and blue is turn right. And my student and color from green to red, and if red recognize, then drone change direction, turn right, and if white finds, then drone stops. And this is my first implementation, and the circuit size is very small, if you know FPGA, this color detection and the drone control, with one microchip, but anyway, around 300 lookup table is sufficient for this drone direction decision. And then color is color has sometimes make error because of the light condition. Therefore, currently we develop marker detection. And if marker normally the circuit size will increase, but currently we proposing some how can I say this? Efficient analyzing method. Therefore, the circuit size is almost same as color detection. And also this kind of technology is adapted to the agricultural drone. And this is the medium-sized drone, and we detecting the crops height in the real time. And this system is currently Iman-san, Dr. Iman developing, and I think he continued to develop this kind of project. And first, I can say this group 1 is grow logic and sensing is probably we can propose a good power efficiency and also functionality. So if we focus on the small and embedded time systems, we can use FPGA. And next is here, the AI, OT, and edge computing. Some people say SoC, system on chip FPGA, because this FPGA has normally ARM or some x86 or some kind of CPU on FPGA die. Therefore, we can implement it some integrated system. And here also I would like to introduce our system. This system is FPGA-based immersive visual display. And this display is developed for remote control remote vehicles. And first is これは次の方を見た方がいいな。sorry, is first this is eye trackers. And this is we can detect the eyesight and eye direction. And then maybe you can see the circle. And first is FPGA captures this eye direction, eyesight, and then the FPGA calculates the position and show the eyesight. And then this kind of interface is very good for the remote control system, and this is communication and computation latency. If we can implement this on the wire, then the total latency is around 227 microseconds. So the camera size is computing and sending the data by wired, and also calculating and show display. Yeah, so FPGA and computation time is too small. But if we implement this on the wireless network, yeah, so around 4.2 millisecond is required for the wireless communication. At the time, yeah, this delay is too large. And especially if we consider the camera delay and projector's delay, especially projector delay is too large. Around 70 to 80 milliseconds is required for sending and showing the frame. Therefore, currently, we developing we are developing new system. Use a high-speed projector and also the high-speed camera. And if we don't use the projector, we use the high-speed display. At the time, we already achieve around 5 millisecond image transmission between the between the several 10-meter situation. And then, yeah, I have to emphasize this kind of FPGA can achieve low latency processing. If we focus on the low latency, especially the less than 1 millisecond, then GPU cannot achieve such kind of computation. So FPGA can survive and FPGA can use in such kind of application field, I think. The next one is here and a large system, rapid prototyping, specialized computing. This is also a traditional FPGA, large traditional FPGAs. And not only embedded system, but also HPC is my target. Therefore, I propose a high performance FPGA-based system. And this system was exhibited in the supercomputing 2019. And this performance signification is around 1.2 terabps network bandwidth. Yeah, here, 100 gigabps and 12 channels, and also the 700 to 68 gigabps storage access, and up to sorry, not 2 terabyte, 2 petabyte. 2 petabytes storage capacity. So this is very powerful system, and we can use this for not only data storage, but also the quantum simulations. And this is the triple storage board, revision 1 and revision 2, and currently using revision 2. So we implemented the quantum simulation on this system. But one big problem is portability, data portability and program portability. So we can propose and develop our own FPGA system. But a development environment, not only FPGA, but also FPGA system is required. So if we do not prepare the development environment, then no one use that. Therefore, currently we already propose not in-house driver. We propose and we deliver the open source drivers and open source framework. And currently, we joined LightX project, and this is one famous open source vendor independent integrated framework. If you are interested, you can access here, github.com, and enjoy digital and LightX. And especially my students committed this project, and currently you can you can find so his name on the so right SATA. Yeah, this project. Now so with open source SATA IP. SATA IP, SATA project, and this is so supporting RAID 0 and so RAID 1. And yeah, not so complicated, very simple, but so this is a product diagram of the trifoil storage board. And this is the so files, the so physical, so I/O and connected to the so SSDs. And here is so right SATA core. And my student so updated, yeah, some bug was found, and so he updated, and also so he implemented so hot plugging functions. And here is some right benchmark and read benchmark are loaded, but here is so user circuit part. So if you added here your original circuit here, this system work well. And yeah, this is so measurement environment, and yeah, this is so 8 times so 2 terabyte SSD and so DMA and the storage subsystem. This is so version 1, but anyway, so we can so measure not simulation, but so this so real environment. So we already so implement. And so storage access speed analysis are very good, and the overall transfer speed and the integer transfer speed is also fine. Yeah, but this please check so here and around so 540 a bit so decreasing, but the smallest access case is so more than so 500 megabyte per second. If you use so SATA SSD, then so I think so this performance is so very good. And also the so read is so around so 570. This so read performance is so almost same as the specification sheet spec, so theoretical spec. Therefore, so we think this is so very good achievement, and also the so power consumption analysis we did. Currently, so our system is not good for the power performance because so power saving feature and smart is not implemented. And but so this is the future work, but so only focusing on so performance, we already so achieved so good performance, and this is so successful implementation and so quantum simulator. Sorry, this is so only Japanese, but we press release by the so Keio University and also University of Tsukuba. And we achieved some 40 qubit, over 40 qubit, so quantum simulator. So if we would like to implement it 40 qubit simulation on the traditional computer, then so probably you need a so large supercomputer. Even if we use Japanese flagship computer Fugaku, 46 or 47 qubit is the max. So that's the so limit of the so simulation.
I'm sorry, Sensei,
Yeah.
4 minutes late.
Okay, and therefore, so anyway, so low latency and so high performance computing, so we can use in the so largest computer. And last one is so extreme for integration here, and maybe so some people also are interested in so particular accelerator sensors. Now, so we so Japan is so developing so new particle accelerators in Hitachinaka, and currently so we are committing with a COMET, so muon electron transition project. But this requires this requires huge parallel sensing systems. And that sensing system output data around 30 gigabyte per second. And also the system continue to work around 550 days. Therefore, the 400 petabyte data storage required. And also the computation. Total computation is more than 5 days of Japanese flagship computer Fugak. Therefore, they would like to they would like to develop the new sensing system, and currently this is developing by us using FPGA. And currently, this is under constructing. Therefore, if next year, we would like to produce that. Then, I would like to introduce our new system again. And this is summary, and I review and provide overview of FPGAs. And the FPGA offers promising advantage in terms of low power consumption, low latency processing, and power performance efficiency. And so we can classify the FPGA in 4 groups, and no FPGA with FPGA, no CPU with CPU, and small size and large size. And so one is includes group logic and some computation. And so probably this group is good for life. And to represent main battlefield, moving forward. But attention is needed because regarding competition with CPU and especially mobile GPUs. And 3 is very nice area, but this FPGA, this kind of FPGA may disappear because we have maybe no new FPGA around 4 or 5 years. And 4 is still experimental, and the hardware is very powerful, but it to be fully utilized. So thank you for your attention. Any question and comment?
Okay, thank you very much, Professor Yamaguchi, for giving us insightful presentation. So before I give a chance to all audience to raise their question, I would like to give some conclusion. So according to presentation, there are a lot of various applications of FPGA. For example, from supercomputer, assistant, video and image processing, drone, embedded system IoT, until quantum simulator and particle accelerator. Okay, to all participants, for those of you who have questions, please raise your hand, or you can type the question on a chat box. Okay, while we are waiting for the question, since I would like to ask, for us who lives in developing countries, could you please explain why the price of FPGA is very expensive, especially for the high performance computing? Because when we buy in Indonesia, the cost become doubles or even more. So could you please explain why the price of FPGA is very expensive?
Currently, FPGA price, not only FPGA price, GPU price is also increasing and increasing. And one large FPGA is around 50 to 60,000 US dollar, only one chip. But one problem is not so many people obtain such kind of large FPGAs.
I see.
Okay. Therefore, for example, if you buy this is one example, but if you buy the Zynq processor around 100,000 units, then probably the price is less than No, now around so why 500 to 1,000 US dollar, I think.
Oh, I see.
But if you buy so one the Zinc FPGA, then probably the price is around at least 3,000 US dollar.
Oh, I see. So,
Mm.
okay, the more cheaper. Okay. Okay, I have one. We have one question from Mr. Widya Budiawan. He asks a question of how does the power consumption profile or of FPGA impact their performance in power sensitive application, and how to optimize for mitigating power usage while maintaining functionality. Okay, Sensei, please answer.
Yeah. Yeah, that's a very good question. And first is so so FPGA research, FPGA researchers don't believe the so simulators value because the so simulation value is so not real and so very valid. Therefore, the so first so we implemented the system on the so real system and measure. And then, so how do we improve? Because in some cases, the beginner, student first start to implement it, their own circuit using HLS, high-level synthesis, so high-level language like so OpenCL, and then OpenCL is so very good for developing so designs in short time. However, it's not good for the optimization. Sometimes the OpenCL code makes very long circuit. After that, first we check the behavior, and then we optimize from we optimize using HDL, hardware description language, like Verilog or VHDL for the power performance optimization. Is that okay?
Okay, is this okay? Okay, thank you very much, Sensei. Because of the time limitation. So
Okay.
once again, on behalf of organizing committee of ICRAMET, would like to thank you very much for giving us insightful presentation.
Thank you
And
very much.
finally, please MC as a token. We will give a token of appreciation, Sensei.
Yes. Yeah, but
Okay.
thank you very much. So
So
thank you for
this
this
is
good opportunity. Yeah.
okay. Once again, please give applause to our distinguished speaker, to Professor Yoshiki Yamaguchi. So on behalf of organizing committee, would like to give you a token of appreciation. Thank you very much, Sensei.
Thank you very much.
Okay, please, I will give back to MC. Right.
Thank you, Professor Yoshiki Yamaguchi, for sharing his expertise to us. And also thanks to Dr. Iman Firmansyah for having moderated this session. Now we're going to start the parallel session of 7, 8, and 9. As I mentioned before, the parallel session 7 will be in the breakout room 1, parallel session 8 will be in the breakout room 2, and the parallel session 9 in breakout room 3. And as usual for presenters, I would like to remind you several things. First, to keep the naming convention according to the guidelines. I also encourage you to stay logged on during the short break. For the presenters that are in their assigned sessions, please turn on the video for the whole session. And please have your presentation slide ready for the question and answer session. And I would like to remind you, and this is regarding the completion of publication with IEEE, it is mandatory for you to attend your question and answer. And also it is mandatory for you to fill in the attendance form as the presenter during your parallel sessions. And for all the participants who want to ask some question during the Q&A, please use the raise hand menu or type in your question in the chat room. There will be a short morning break, but still, we're already behind the schedule around 5 minutes. So the duration for the short morning break will be different for each breakout room. So I would like to encourage and to remind the moderator to please to keep the time as close to the schedule as possible. So I would like to all of you to start the presentation of 10, 11, and 12 at 10:40 a.m. So please stay in your breakout rooms. And for the last parallel session of 13 and 14, there will be 2 breakout rooms for this, and it will continue after the lunch break at 1 p.m. at GM777. And for all participants and presenters, please enjoy the parallel sessions.
Recording stopped. Recording in progress.
Good morning, everyone. Welcome back again with me, Iman Firmansyah, in this parallel session. So, because time limitation, so first of all, I would like to thank for joining us today, this morning. So, before we get started, I would like to confirm that all presenters are joining us this morning in this session. So please let me ask you one by one. For the first presenter, Mr. Sahrok Hamidi, are you joining with us?
Yes, hello.
Okay, hello, assalamualaikum, thank you. So for the second presenter, Mr. Afab Rifai from...
Yes.
Okay.
I'm here.
Okay, that's great. And then for the third presenter, I guess this is the same presenter, Mr. Sahrok Hamidi. Is that you?
Yes, it's the same. Yeah, yes, exactly the same presenter.
Okay.
Thank you so much.
Okay. That's great. Okay, thank you. And then
Thanks. Thank you.
For the fourth presenter, we have Mr. Akib Rahmatillah. Are you joining with us today? Are you there?
Yes.
Okay, thank you. And then for the fifth presenter, we have Mr. Mustafa Kucuk. Are you there?
Yes, I'm here. Thank you.
Okay, that's great. Okay, thank you. So, as you know that we have a 10-minute presentation and 5 minutes for the Q&A session. So, without any further ado, so please welcome for the first presenter. We will play the recorded video, and for the first presenter, please stand by. Okay, for the MC, please play the recorded video presentation.
Hello, everyone. My name is Shahrukh Hamidi, and the topic of my presentation is multispectral based imaging with application to millimeter wave imaging at W band. First off, I'm going to start with the goal of our paper, and then I'll present a model geometry. I'll then talk about the image formation and image denoising. Then I'll present a subband stacking, which is the main topic of the paper, and I'll present a system model along with the experimental setup. which is based on our own custom-made wideband FMCW radar. And then I'll present the experimental results and I'll conclude the presentation at the end. Well, the goal of the paper is to create RGB images from radar data to be used for material characterization. The geometry of the model is based on a 1TX1RX FMCW radar, which we move it along the azimuth direction in order to create the effect of a large aperture synthetically. The image reconstruction algorithm is based on the back projection algorithm, which I have presented here. The goal is to estimate the radar cross-section of the target. And then for image denoising, I have implemented the state-of-the-art Perona-Malik diffusion technique. The implementation is based on Euler-Lagrange technique in Python. So the subband stacking, which is the main topic of this paper, is based on dividing the entire bandwidth into 3 equal subbands. Per each subband, we create an image. We then perform image denoising, and then we put all those 3 images together over an overlay of all of them and present them as the RGB image. So basically, the way that it works is just each subband is basically treated as a separate and specific part of the signal in order to be used to create an image. And this stacking is done basically at the IF level. We don't have access to the RF signal. Everything that you see actually is done based on the IF signal, which is also known as beat signal. So in this slide, we present the block diagram of our wideband custom-made FMCW radar. We have an FMCW PLL, which generates a signal from 12.5 to 18 gig. The output power is approximately 10 dBm. Then we have a doubler and a tripler in order to increase the frequency of the signal to 75 to 108 gig. And then the output of the signal is approximately 10 dBm. We have a power splitter, which sends a portion of the signal to the TX antenna and then another portion to the RX side. On the RX side, we have an LNA with 25 dB gain and 4 dB noise figure. And we have a mixer which mixes the received signal with a portion of the signal that we have already transmitted in order to create the IF signal. And then after that, we have a high-pass filter. The purpose of the high-pass filter is just to remove the energy of the signals that are really close to the radar, and also to block any leakage that we have from the TX into RX. Basically, it's just to protect the receiver from high-energy signals. Then we have IF amplifiers in order to map the signal to the full scale, basically ADC inputs. And then we have the ADC to generate the digital signal for us, which we can use for image formation and subsequent digital signal processing stages that we have. The impulse response of the system has been presented here. It gives us, with 33 gig bandwidth, we get almost 5 millimeter 3 dB range resolution, or resolution limit of the system in the range direction is going to be 5 millimeter, based on this experimental results, which is based on data that we have collected from a trihedral at 1 meter radial distance. In this slide on the left, you can see the power spectrum of the system from 75 gig to 108 gig, which is the full 33 gig bandwidth of the system that we have developed. As you can see, at the beginning, we have a deep null. And towards the end, we have power fluctuation. So power fluctuation basically is going to blur the image. And we have to stay away from those portions of the power spectrum that we have power fluctuations in. And in order to be able to perform very high resolution imaging, what I did was I just focused on a specific part of the bandwidth which doesn't contain huge amount of power fluctuation. So instead of 75 to 108, I chose 78 to 102 gig. And as you can see, the maximum power fluctuation that now I have is 7.84 dB, which is acceptable based on the results that I'll present later. So basically, instead of 33 gig bandwidth, now the effective bandwidth of the system is 24 gig. And the only reason was because we had a tremendous amount of power fluctuation, which we can't really deal with. So the subband stacking, which is the main subject of this paper, is based on dividing the entire bandwidth into 3 equal subbands, as I said before. Now with 24 gig effective bandwidth that we have, we divide the entire 24 gig into 3 subbands. Each is going to have 8 gig bandwidth. And then we assign red, green, and blue colors to every single one of them. Basically, we take the 78 to 86 gig subband and assign the red color to it. We create an image, we denoise the image and assign red color to it. Then for the 86 to 94 gig subband, we create another image, we denoise the image, and then we assign green color to it. And for the third subband, which goes from 94 to 102 gig, we create the final image, and we denoise it and assign the blue color to it. Then we use all 3 of them. An overlay of all of them is going to provide us with the RGB image that we're looking for. In this slide, we have presented our experimental setup. It's our own custom-made wideband FMCW radar with 33 gig bandwidth. As you can see on the left-hand side, actually, we have presented an image from the radar system. We have used open waveguides on both TX and RX side. We can use horn antennas as well. And then we have the LNA mixer, ADC and synthesizer, which I have highlighted them. And then on the right-hand side, you can see the radar system, which we have mounted it on this axis motor in order to be able to move it horizontally to create the effect of a large aperture. The aperture that we have created has 40 centimeter length, and that's the exact same length that we have used for all the images that we have basically created in this paper. Well, the result of the experimental setup basically for a spherical target in front of the radar has been presented here. For spherical targets, we don't really expect any frequency selectivity, which means per each subband we should get the exact or very, very close basically radar cross-section, which means the radar cross-section per each subband should almost be the same. And as you can see, per red, green, and blue color, we get almost the same RCS. The value for the absolute value for the RCS is they're very, very close, which means if I combine them and if I overlay all red, green, and blue color images and I show them as an RGB, as you can see it on the bottom right, you should see a white image. And as you can see, actually, is the image is white, which shows that a spherical target basically doesn't show any frequency selectivity. After that, we used a bike as a very complex target, which has been composed of so many different point reflectors. We have frequency selective reflectors here, basically. And on the right-hand side, you can see, on the left-hand side, you can see the experimental setup, which is the bike in front of the system. On the right-hand side, you can see the reconstructed image based on the back projection algorithm, which is noisy. The dynamic range that I have shown is 50 dB in order to see the background noise. And then I denoise the image, which you can see the denoise image on the bottom left based on the Perona-Malik algorithm. So on the left-hand side of the slide, you can see the denoised image. Per every subband, we create an image like this, and we denoise it, and then we assign red, green, and blue colors to them, and then we show the overlay of all those 3, and that's going to be the final RGB image that we're looking for, which I have presented it on the right-hand side. The only thing that I should mention here is I performed a little bit image enhancement in order for better visualization. I also, instead of showing the absolute value of the image, I presented the 1 minus absolute value of the image. So what you see on the right-hand side is 1 minus the absolute value of the image. The only reason was to just for better visualization. Other than that, there was no specific reason for that. So basically, if you have a point reflector which is not frequency selective, which means it has a flat frequency response over the entire bandwidth, we should see it as black. And if you see some point reflectors that are not black, it means they are frequency selective point reflectors. That part of the material is going to be frequency selective, and that's basically the application of this technique in material characterization. Well, to conclude the presentation, I should say that we presented high-resolution millimeter wave imaging, 2D high-resolution millimeter wave imaging at W band. We performed image creation, image formation, and image denoising. And then we performed subband-based imaging. And the main goal was to create RGB images for radar data. and to basically to be used for material characterization to see whether the target shows any frequency selectivity characteristics or not. And then at the end, we used our own wideband FMCW radar system to present the experimental results based on. Thank you so much for your attention. And if you
Still mute.
Okay, thank you. Thank you. Okay, thank you very much for the nice presentation. So we will open the Q&A session. For those of you who have questions, please raise your hand. Is there any question? Please let me check the chat. Okay, while we are waiting for the participant to raise question, so I would like to ask, that was interesting research. So my question is, could you please give us detail of the hardware specification, for example, in ADC and CPU? How to process?
right, yeah, the ADC, the sampling rate for the ADC was 5 megahertz. The chirp time that I chose was 5 milliseconds.
I see.
And right, of course, there wasn't any specific reason for 5 milliseconds, for example, or 5 megahertz. 5 megahertz is because the target was really close to the radar. I didn't want to do oversampling. I wanted to keep the number of samples low. So this way I was able actually to do the processing faster. For the 5 milliseconds, I could have actually chosen a little bit lower than that. The reason was 5 milliseconds is because I was able to get extra gain from it. Basically, when the average power that I was able to get from 5 milliseconds was much higher, basically, let's say compared to 1 milliseconds. And of course, you cannot really go faster than a specific limit, for example, 100 microseconds, because your synthesizer won't be able to give you 33 gig bandwidth over, let's say, 100 microseconds. There are limitations actually when it comes to hardware, but I was able to go to all the way to 5 milliseconds, and I did it on purpose is because I wanted to get gain from the 5 milliseconds. I wasn't able to go beyond the 5 milliseconds. That was the limitation. So what I did coherent averaging over 100, basically 5 milliseconds, in order to increase the gain, because at that frequency the path loss attenuation was really high.
Oh, I see. So one more question. So how to avoid the bottleneck? I mean, did you use a PCI Express based APG, ADC?
The synthesizer actually that we had, that I showed in the image, it had the ADC inside it. It was just a full package, basically. ADC synthesizer. It was in one package, basically, and we purchased it, and we only set the ADC sampling rate to 5 megahertz, and then the synthesizer, you just program the synthesizer, and it was like a discrete system that we built. So you have the synthesizer and ADC, and then the rest was just the mixer and LNA, and we put them together. It was like a lab experiment, basically. It's a discrete system that we built.
Okay, that was good. Okay.
Thank you.
To all participants, is there any question? So basically, I would like to ask you more questions, but because of time limitation. Well, I guess there is no more questions. So finally, please give applause to our distinguished speaker.
Thank you so much.
Thank you very much for giving us insightful topic.
Thanks. Thank you.
Okay, thank you very much. Before we continue to the next speaker, please, on behalf of organizing, we have to take how to say, a picture, the participant picture. Please, to all participants, turn on your camera. The MC will take the picture. MC?
Yeah.
Okay.
Yeah. Are you ready? Okay, the first slide. 3, 2, 1. And then the second slide. 3, 2, 1. Thank you.
Okay, thank you very much for taking a picture. So for the next presenter will be delivered by Mr. Apap Rifai.
Yes.
Okay. Please stand by. We will play recorded version of your presentation. Okay,
Okay.
thank you.
For the time, I want to present my research. Let me introduce myself first. My name is Afwadil Rifai. I want to present my research about PI sliding mode control on a hydraulic thermometer testbed. This research background, according to traffic environment simulator, is one of supporter on electric vehicle development, and then this traffic environment can be realized as a road load. The traffic environment can be made with hydraulic thermometer testbed, this laboratory scale, and then to make a match with traffic resistance, we can adjust the motor test loading condition. This research objective is first to representing the traffic environment as a road load on a hydraulic thermometer testbed, and then after representing the traffic environment, the controller is made to made as fast as possible to follow the reference start on a road load. This research method have three big methodologies. First, we developing the model based on nonlinear constraint. Because of the model with nonlinear, we can see the hydraulic effect of testbed, and then we can use a nonlinear controller with HDTP, and then we can comparing the linear control. We use PID, and then we compare with PASMG as a nonlinear controller. In this flowchart, we make collecting characteristic to make a road load, like wind speed, speed of motorcycle, and then we building a model with identification system, and then we use PID to control the dynamometer, and then we can compare with PASMJ to improvement. And then after that, we can tuning the controller to respond the traffic environment condition. The traffic environment condition have so many parts, but we simplify with F-drag. F-drag is according to average air density, and then drag coefficient of motorcycle, and then the cross-sectional area of motorcycle, and then we see the relative wind speed. After we have F-drag, we can multiply with a tire to make this set point as a torch. This hydraulic dynamometer have a motor test to make the dyno is rotating, and then the dyno is connecting with load cell as output. The gear pump is used to make a hydraulic oil flow, and then stepper motor on a rotary valve is controlling the flow. This is the identification system is comparing the input and output on a stepper motor rotary valve, and then the load cell as a torch reference. This is the state space of system. And then we use PISMJ. PISMJ have control signal as U equivalent and UN. U equivalent respond with KP and KI, and UN respond with epsilon and signum. This is the nonlinear constraint of a system. We have a saturation value of stepper motor 10.5 turn, and then the hydraulic valve has the zone 2. This for turn after the hydraulic valve is read by sensor. The relay transport is shown with 4.7 from input valve on a control valve to load cell as a reference. This is a delay because of flow on a hydraulic system. This simulation, we have change the value of KP from 10 to 40. We have choose the KP at 30. This response is after looking the implementation, we have the simulation is as good as implementation. The implementation, we have the Lundberger estimator as a state of X, and then we have control signal from Arduino Uno. We have a control panel to make this system is good to control the control valve. And then the result, according to simulation actual, this simulation have rise time 30.06 second, and the actual is 16.71 second. This is according to step info at MATLAB. This have same response with actual and simulation, but still cause oscillation on a steady state condition. You can see the system, you can see the response have so many oscillation on steady state condition. And then we can compare the PISMJ response to PID. The PISMJ have a good rest time, but the research is to minimize the oscillation is need the improvement. Closing remark, HDTP model is describe single throat load 0.7 has been created using state space, and then the PID control it's good to control the HDTP, but the PISMJ controller is make it better. The HDTP control using PISMJ has better response rest time and better setting time, but has also have oscillation at a steady state. The following research to improving the steady state oscillation condition is necessary. if PSMC control is to continue to be used in this HDTP. Okay, that's all. I want to end this presentation. Thank you.
Okay, thank you very much. That was nice presentation presented by Mr. Apap. So we have one question from Mr. Akib Rahmatillah. So the question is, what was the sliding surface equation that you chose?
Okay. Thank you for the question. I use method with KP and KI, and then I choose the response is the objective is to as fast as possible. So the sliding surface is not yet show, but with the KP and KI, this control signal is used to control the hydraulic test bed. So the answer is I'm not yet to calculate the sliding surface.
Okay, thank you, Mr. Akib. How about the answer? Are you agree or you have another question? So while we are waiting for another question, I would like to ask. Okay, thank you. So I would like to ask one question. So you
Yes.
mentioned on the presentation, the result, the delay is how to say 4.7 second until 16 second. So what kind of is it possible to reduce the delay? So in my opinion, the how to say 16.7 second is a little bit slow.
Yes, yes. I know. So the next objective research is to reduce the delay, of course. We in this existing test bed, we use a motor stepper as a control to control control valve, and then after that, first I think we can use a motor DC to control valve. Uh, we call it rate constraint, and then motor DC can break the rate constraint of the motor. So with fast respond with for at motor DC, we can break the rate constraint of motor stepper. And this is first, and then the second solution, uh, I will make this existing test bed use fixed pump, gear pump, and then I will make it with flexible pump or sway split pump. So the response, uh, I think we can use it to reduce the delay at hydraulic test bed.
Okay, I see. So maybe I would like to suggest maybe you can reduce the delay by using another microcontroller, for example, the
Ah, okay, okay.
Arduino, which has 32-bit or
Okay.
I
Yeah.
think.
Uh, it's it's not on my choice because I focus at the method and the test bed. I think I will use like maybe from National Instrument and LabVIEW. Okay, thank you for the suggest.
Okay, thank you very much for the answer.
Yes, yes.
Okay, but anyway, okay. Thank you once again for your nice research. So, and then for the next presentation, it will be delivered by the same presenter. So this time, Mr. Sahrok Hamidi will present The study, the title is IQ Imbalance Compensation and Block Sparsity-Based Harmonic Analysis with application to vital sign estimation using CW radar system. Okay, to the MC, please play the recorded presentation.
Hello everyone, my name is Shahrukh Hamidi, and the topic of my presentation is IQ imbalance compensation and block sparsity-based harmonic analysis with applications to vital signs estimation using CW radar systems. So we're going to start with the goal of the paper, why I wrote this paper, what was the reason for it. Then I'm going to present how to perform vital signs estimation based on CW radar technologies. I'll present everything in detail. I have presented everything in detail in the paper. And then I'll talk about the INQ imbalance issue. There are three effects that I have talked about them in detail. And then I'll basically, I have presented least squares based approaches in order to compensate for the INQ imbalance. And then I talk about the harmonics of the breathing signal, which they're going to be of high importance here, and how to deal with them. And then I'll present the experimental results based on the data set that I basically received, downloaded from Oxford University's website, is publicly available for everyone. And then I'll conclude the paper. So the goal of the paper is twofold. One of them is to present vital signs estimation procedure based on CW radar systems, and then to address INQ imbalance and estimating the heart rate in the presence of the strong harmonics of the breathing signal. So CW radars, they have a very simple structure, and in a CW radar, the received signal from a subject under test can be presented as S of t that I have presented here. RT is the instantaneous radial distance between the subject under test and the radar system. And the phase of the signal, which contains the information that we need for vital signs estimation, is phi of t. And when we have the back and forth motion of the chest and heart, they're going to modulate R of t, and that's exactly the information that we need in order to estimate the heart rate and breathing rate. So the phase estimation is based on arc tangent of Q over I. We have quadrature and in-phase channels, and then we take Q over I and we perform the arc tangent, and this way we can get we can estimate the phase of the signal, which we will be using it to estimate the heart rate and breathing rate. So when we look at the INQ channels, unfortunately they're not just cosine of phi of t and sine of phi of t. The gain, DC level, and the phase of channels are going to be different. So we're dealing with amplitude mismatch, phase mismatch, and DC mismatch. In the paper, I have presented the full structure of how to deal with this INQ mismatch, INQ imbalance basically issue. It's just based on least squares based approaches, back-to-back least squares approaches that I have presented in detail in the paper in order to compensate the effect of all these three basically issues that we have. Another issue that we face is the strong harmonics of the breathing signal. The breathing signal is before the fundamental frequency of the heart rate, and its harmonics are going to be strong, and they're going to interfere with the fundamental frequency of the heart rate. In order to be able to cope with this issue, I just came up with this convex mixed integer programming algorithm that I have presented here, and this is going to take care of that issue. The experimental setup that I have used in this paper is based on the data which has been gathered based on a CW radar. It consists of 24 hours of synchronized data from a radar and a reference device. The reference device here is an ECG device that I use as the ground truth. The implemented CW radar system is based on a 6-port technology and operates at 24 gig in the ISM band. I didn't collect the data myself. I have cited the reference. It's from Oxford University, and you can see it at the bottom of this slide. And it's basically available for anyone who wants to download it. Well, the experimental results that I have used, it has INQ channels, and when you look at the INQ of one of the experimental data sets that I have used, you can see the imbalance clearly on the right hand side. When you look at the quadrature versus in phase diagram, you can see an ellipse which has been tilted. When you have an ellipse, it means that the gain of I and Q are not equal, and when we have a tilt in it, it means there's a phase discrepancy between I and Q channels. And when we have this center of the ellipse is not at 0, is not at 0 and 0, which means it's not at the center of the coordinate system. It means that we have non-zero DC values, and as you can see, these DC values are different for I and Q channels. So on the left-hand side, we can see the uncompensated I and Q diagram. In the middle, we have the phase compensated results. When we compensate for the phase, we remove the tilt of the ellipse. And on the right-hand side, top right, you can see the DC compensated as well. So after DC compensation, you can see the ellipse now sits at 0 and 0, which means at the center of the coordinate system. And at the bottom, you can see the phase DC and amplitude compensated result. When you compensate for the amplitude, you go from an ellipse to a circle, which means now the gain of both I and Q channels are equal. So when we perform the compensation for all those three basically effects that we had, we go from the I and Q diagram that we have on the left to the one that which we have shown it on the right. After that, we can calculate the phase of the signal, which is arctangent of Q over I, and I have presented the phase of the signal. This phase, ideally speaking, only contains the effect of the chest movement and heart movement. Of course, if you have any extra motion from the body, you can see it here as well. There's a downward trend here that you can easily see it, which we have to remove it. It has a very negative impact. After that, you can take a Fourier transform in order to go into frequency domain and see what kind of fundamental frequencies we have. So if we perform Fourier transform, you can see that graph on the at the top of the slide. Unfortunately, because of the downward trend, we can't get a very strong fundamental basically result for the heart. So what I did was I performed one lag difference, which means instead of S of t, I just used S of t minus S of t minus 1 in order to get rid of that downward trend that I had. Then I took another Fourier transform from this one, and on the bottom right, you can see the result of applying Fourier transform to this signal. And now you can see that the fundamental frequency for the heartbeat is much more pronounced. So after performing the Fourier transform, we take all those peaks, which contains the fundamental frequency for the breathing signal, as well as the fundamental frequency for the heart rate, and all those harmonics that they have, and we feed them to this mixed integer programming optimization problem that I presented here. So X here is the vector that we are looking for. It can only take 0 and 1 values. When it's 0, it means we don't have any fundamental frequency at that frequency component. When it's 1, it means that that frequency component represents the fundamental frequency of one of the signals that we have in our, basically the phase of the signal that we are processing. And since we only have limited number of sinusoidal signals, so I enforce sparsity. The way that I enforce sparsity is using the L1 norm of X, as you can see it, in order to make it convex. And then you can easily solve this optimization problem in, let's say, CVXPy in Python. That's how I solved it. Or CVX package in MATLAB, or any other packages that you're familiar with. It's a convex optimization problem, so you can get the global minimum for it. Signal. The result of solving the mixed integer convex optimization problem has been shown here. As you can see, and as I said, we have only 2 non-zero values for X. And one of them is at 0.37 hertz, which is the fundamental frequency for the breathing signal. Another one is 1.18 hertz for the fundamental frequency of the heartbeat. In order to validate the accuracy of this for the heartbeat, I just looked at the result of the ECG signal. As you can see, the ECG signal itself, of course, is not going to be a completely stationary signal. So what I did was I took the ECG signal and I performed peak finding, and then I looked at the interval between every adjacent basically peaks. They weren't exactly equal, so I took an average over the course of 20 seconds, and then that average gave me 1.18 hertz, which confirms the same value basically that I got from the radar, which is 1.18 hertz. So to conclude this presentation, I should say that I presented vital sign estimation based on CW radar technologies in detail, how to perform that. Then I addressed the INQ imbalance problem, and I presented least squares based approaches to compensate for INQ imbalance. I then talked about the harmonic issues, the strong harmonics of the breathing signal and how they can impact the fundamental frequency of the heartbeat. And then I presented this this approach based on a convex mixed integer programming optimization problem. At the end, I actually used the experimental data that I got from the Oxford University, and I applied these algorithms to the experimental data, and I presented the results, and I used the ECG device, the signals from the ECG device as my ground truth to show the accuracy of the algorithms that I presented in the presentation. Thank you so much, and if you have any questions, please feel free to ask me. Thanks.
Yeah, okay, thank you very much for Mr. Sahar Hamidi for the second presentation. This time, he focused on radar for vital sign estimation. So to all participants, for those of you who have questions, please raise your hand or you can type question on chat box. Okay, while we are waiting for question from the participant, once again, I would like to ask you, Mr. Hamidi, Sahar Hamidi. So I was wondering because from the viewpoint of hardware, how can your system detect the vital signal estimation? Because as we know that vital sign is very small. I mean, small.
Yes, absolutely. So the range of the chest movement is about a few millimeters up to 12 millimeters. Let's say 3-4 millimeters up to 12 millimeters. If you go into deep breath, for actually heart is about 0.1 millimeter to 0.4 or 5 millimeters. So it's really, really small, that displacement. So that's why they use millimeter wave radars. Previously, I was using 77 gig radars and 60 gig radars myself, but I didn't have that reference signal. It wasn't a controlled environment, so that's why I didn't use that one. This one was 24 gig. So when you look at the wavelength of the signal in 77 gig or 24 gig, it's about a few millimeters. In this case, I guess it's about 12 millimeters. So that small displacement still compared to the wavelength is quite a lot, which means it gives you enough phase shift that you can sense it. If you go to very, very low frequencies, your wavelength is going to be really huge, so you can't sense that small, basically, phase shift that you get. That you're absolutely right. That's why we go for higher frequency. So the higher the frequency is, the smaller the wavelength is, which means that small displacement actually can be sensed easily. So the phase shift that you get from the both heart rate and breathing, basically, at 77 gig, we have 4 millimeter bandwidth wavelength. At 60 gig is almost the same. I guess at 24 is about 12 millimeter or something like this. So when you look at the small displacement, it is small, but compared to the wavelength, still it creates enough phase shift for you that you can sense it. And you could clearly actually see from the diagram of the phase that I showed that you could clearly actually see the breathing and even heart, actually a small peak on those cycles, basically.
Okay, thank you. I see. So the key is by using millimeter wave, right? So, and how about the amplification?
Excuse me, I didn't hear this one.
And how about the amplification? I mean, to amplify the signal. Did you use that method?
Amplification of the signal? There is no amplification of amplification of the signal. When I was doing it myself, actually, I was standing right in front of the radar at, let's say, 30 centimeters or 1 meter. This one also, the distance was almost at that range, actually. So at 1 meter or 30 centimeters, actually, that was the distance between the radar and the subject and the test. And you can, with the existing chips, like, for example, Infineon or from Texas Instruments that I've used all of them, actually, you have enough power basically at that range to get a very strong signal, strong enough actually that you can sense it and you can do your analysis over it.
Also, how the circuit inside one chip, right?
The TI and Texas Instruments and Infineon, actually, the whole radar is just one chip. In the case of Infineon, and you have a DSP on top and everything, actually. This one that I have comes from Oxford University. I didn't collect it myself. It was not a chip-based radar. They just built a very discrete system. And as you can see from the I&Q, the quality of the system wasn't quite good, actually. So it was an experimental system. They built it. It was a group of several people at Oxford University, but the data was publicly available. The good thing about this was it was actually performed under controlled environment. So they not only they took the radar data, but at the same time they were collecting data from PPG and ECG signal as well. So I used the ECG signal as my ground truth. When I was doing it myself, I was just doing it without any control or anything like this. That's why I couldn't use my own signal, actually. But this one comes from a very controlled environment. I downloaded it in 2021, actually. I started this work in 2021. So I guess it's available. Yeah, and I have cited the reference. Basically, you can go and download it. It's quite a lot of data set, actually. It's not just one. So many of them from the back, from the front, actually, for different people. Yeah, they've collected the data sets.
Okay, thank you for the information. Okay, once again, thank you for delivering the nice topic in this conference.
Thank you so much. Thanks. Thank you
so much. Okay.
Thanks.
Okay, because I guess there is no question, so please let's go to the next presentation. So the next presentation will be delivered by Mr. Akif Rahmatillah from 10 November Institute of Technology in Surabaya. The title is Performance Evaluation of State and Output Feedback-Based Repetitive Controller for Rotational Control System. Okay, please MC play the recorded presentation.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Akif Rahmatillah. I'm a student of the Engineering Physics Doctoral Program at 10 November Institute of Technology, Surabaya. Today, I'm going to present my result of my preliminary study entitled Performance Evaluation of State and Feedback-Based Repetitive Controllers for Rotational Control Systems. For beginning, I want to give an introduction about repetitive control. Repetitive controller is a controller that can track a reference signal or reject a disturbance signal in the form of periodic signal. Like this illustration, where the controlled variable is in solid and the periodic reference in dot. For more details, take a look at the following block diagram. R of T, reference signal, is a periodic signal. Then, repetitive controller will be able to make Y of T, or controlled variable, has the same pattern with its reference without any phase shift, or called effect tracking, like this figure. This happens because the repetitive controller is able to generate a mathematical model of periodic reference in the form of transfer function Is, where Is equal to Qs, low pass filter, times e to the power of minus Ts over 1 minus low pass filter times e to the power of minus Ts. E at here means period of the reference. This block diagram describes the output feedback repetitive controller. Now, I'm going to describe about state feedback repetitive controller. State feedback repetitive controller is one of the repetitive controller topology where two controller gain compensate the state variable of the pen and state variable of the repetitive control system. Repetitive controller in this topology only consists of the low-pass filter and time delay without the learning function. If the low-pass filter is first order with omega f is of frequency of the low-pass filter, then repetitive controller system can be modeled in state space equation like this one, where xf of t is repetitive controller state variables, xf of t minus t capital is repetitive controllers state variables one period before, and v of t is variables of repetitive controller. The control signal u of t consists of two actions. The first one is control action. It means control signal from the current time state variable. And the second one is learning action, which means the control signal from one period before. But this control signal equation has a problem. Because we can see clearly that the control action depends on KP and KE compensators simultaneously. So we are not be able to tune control action and learning action separately. Overcome this problem, the state space model of closed loop state feedback RC or state feedback repetitive control should be transformed to the two-dimensional hybrid model. Two-dimensional hybrid model is model that function of periodic sequence K and time variable in one period tau. Then the two-dimension hybrid model of closed-loop state feedback repetitive control is like this state space equation, where factor x is state variable of closed-loop state feedback repetitive control. It consists of factor xp, the state variable of the pen, and factor xf, the state variable of repetitive controller. After applying the two-dimension hybrid model, the control signal u of t can be written as this equation. In this equation, it can be seen that control action only depends on compensator GP, and learning action depends on compensator GE. However, because in the block diagram, the compensator that can be implemented are KP and KE. The two compensator can be computed from GP and GE using this equation. In the numerical experiment, the mathematical model of the rotation system with input ut, the voltage, and output yt, the rotational speed, can be described as a state space equation like this one. And then, in the term of transfer function, the plan model was like this equation. The reference signal in this experiment was r of t equal to sin e plus 0.5 sin 2 pi t. The alpha value is 1.9 and the beta value is 1.1. It means we want to make a control action more significant than learning action. The omega f, or cutoff frequency of the low-pass filter, was 25 radian per second. We use MATLAB and Simulink for numerical experiment platform. And for solving linear matrix equality, we use YALMIP MATLAB optimization toolbox. The performance of state feedback repetitive control and output feedback repetitive control for the comparison can be seen in the following figure. State feedback repetitive control was able to achieve perfect error tracking after 5-cycle period, with maximum error generated was 0.5146, while the root mean square error value was 0.1229. While feedback repetitive control was able to achieve perfect error tracking only after one period, and the maximum error generated was 1.2908, and the root mean square value error values was 0.2809. From this data, it can be seen that in the term of error parameters, state feedback repetitive control is better than output feedback repetitive control. But state feedback repetitive control has a slower settling time value. The conclusion of this study are the two-dimension hybrid model used this time simplifies the computation of compensator values because the control action and learning action compensators can be designed independently. The second one, although the general repetitive control or output, it's the output feedback repetitive control, can achieve perfect tracking after one period, the error value generated in the state feedback repetitive control is smaller in the terms of maximum error atau peak error and root mean square error. While the state feedback repetitive controller provides smaller peak and root mean square errors, it exhibits slower convergence times or settling time. For my future research, it's crucial to design a state feedback repetitive control that ensure faster and finite settling times. So that's my presentation. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Mr. Akif Rahmatillah, for giving us a nice topic. So, to all participants, is there any question? Please ask to Mr. Akif Rahmatillah. Please wait, I'm going to check whether or not there is a question on chat book. Okay, while we are waiting, Mr. Akif, I would like to ask you one question. So, you mentioned about the repetitive controller. So, did you compare the performance? How good the improvement? So, by using your proposed design compared to the, let's say, normal PID controller, is there any improvement?
Okay. Thank you for the question. Actually, repetitive controller is has a special purposes. The special purposes is the repetitive controller designed for repetitive systems. Repetitive systems mean the systems is controlled by the reference signal or the disturbance signals is periodic signal. if we deploy the PID controller for the repetitive systems, actually I have exercised this problem maybe 2 or 3 years ago, and then the drawbacks of PID controller is the control response is phase lag. It means that when the reference is going too high and the controller, the PID controller response to make the control variable going to high too, but there is a small phase for the response. So the good things of the repetitive controller is repetitive controller can follow or tracking the reference without any phase lag, or it can say the perfect tracking performance. But in my focus, I focus on repetitive controller in a time domain or in state feedback design. Actually, the classical or in the past, repetitive controller is designed in frequency domain. So this is a challenging issue that the state feedback controller has drawbacks in the settling time. So in my future research, I want to design a new form of repetitive controller by state feedback form, but it ensures the settling time is smaller or less settling time than my first numerical experiment in this paper. Thank you.
Okay, thank you much for your answer. Because the time limitation, okay, thank you once again, thank you very much. So we are going to move to the next presentation. So the last presentation in this parallel session will be presented by Mr. Mustafa Küçük from Istanbul Technical University and Aswan AS, Turkey. The title is Novel Square Wave Jamming Strategy for Countering Sequential Lobbing Radar. Okay, to MC, please play the recorded presentation.
Hi everybody, my name is Mustafa Küçük. Today I will present the results of our research on jamming of sequential lobbing radars. I have divided my presentation into 5 sections, which are shown in the slide. Sequential lobbing radars have low cost, desirable hardware complexity, and calibration requirement. That's why they are still used by countries. However, they have poor response to square wave jamming. If we look at the literature, qualitative comments are given by Van Brunt for effectiveness of square wave jamming on sequential lobbing radar. First theoretical analysis is provided by our previous work, which is valid for main lobe region of the sequential lobbing radar. Then the analysis is extended to side lobe region with the third study. If we briefly explain the tracking mechanism of sequential lobbing radars, it uses 2 pencil beams in order to determine angle position of the target. These pencil beams are squinted with a θ0 angle, hence they create a power level difference if the target is not on the tracking axis. Hence, the target angular position can be determined using this power level difference. However, if a jamming signal with amplitude modulation is applied, false target occurs at one side of the tracking axis. Mathematical expressions for the direction finding operation related to sequential lobbing radar with sync-shape antenna pattern is given in the slide. Power levels received at the 2 beam positions due to jamming signal and skin return or platform RCS is given by equations. Here, 2n is the number of pulses within a single angle measurement interval for the sequential lobbing radar. K is the number of jamming pulses transmitted when the radar is receiving with beam position 1. GS is square wave jamming gain, which is related to jamming to signal ratio and phase difference between skin return and platform skin return and jamming signal. Phi t is phase difference between skin return signal and jamming signal. Alpha j and alpha t are voltage levels of the jamming and skin return signals. Traditional square wave jamming transmits jamming pulses to only one beam. We propose a phase reversion mechanism in order to improve this effectiveness of traditional square wave jamming. This creates large angular error overshoots due to underdamped response of the angular tracking loop. Here, the waveform of the proposed jamming signal is given in figure. You can see that jamming starts here, and then it transmits pulses to or signal jamming power into beam 1, and then phase reversion is applied and the jamming signals are transmitted when the radar is transmitted or received from beam 2, and then again phase reversion is applied. Here the power levels is given for the radar for proposed jamming technique. The signal power levels of the transmitted signal by the radar is given in figure A, part A, and then the signal power received by the radar due to platform RCS is given at part B. Signal power transmitted by the square wave jammer is given at part C. Then total signal power received by the radar is given at part D. The power levels when the radar acquires the settling angle is given at part E. You can see that signal power received by the radar due to platform RCS and signal power transmitted by the square wave jammer, and the total signal power received by the radar. Note that the power levels at two beam positions are the same. When the phase reversion is applied, there occurs a huge power level difference between two beam positions, and this creates large angular overshoots at transit region of angular tracking loop, and it will cause a radar break lock at lower JSR values with when we compare it to traditional square wave jamming. Let's look at simulations and discussions. I have given here the simulation parameters for this technique, and the first simulation is done when the JSR is jamming to signal ratio is 10 dB, and we can see that jamming starts here, and the angular error occurs at the transient region. Underdamped response of angular tracking loop can be seen here. The green line also shows the traditional square wave jamming settling angle, and the purple shows the first overshoot, which is also traditional square wave jamming overshoot, and the red line shows the proposed method large overshoots when we compare to traditional square wave jamming. The bottom of the figure shows the power levels of two pencil beams as a function of time. When we increase JSR to 11 dB, we can see that the traditional square wave jamming and the proposed method shows larger overshoots. However, both of the technique cannot break the radar lock. However, the power level differences increases. When we increase more and shows 12 dB jamming to signal ratio, we can see that traditional square wave jamming cannot break radar lock and settle the angle shown with green line. However, when we apply phase reversion, we have seen a large angular overshoot, large power level difference, and it creates a track loss. Hence, our proposed method break the radar lock at 12 dB JSR. And we increase the JSR at 15 dB, and the traditional square wave jamming also breaks the radar lock, as shown in the figure. Hence, we can see that our method improves JSR requirement of the traditional square wave jamming by 3 dB. And our technique, by incorporating phase reversal into the square wave jamming, the proposed method exploits the vulnerabilities in the angular tracking loops, leading to significant angular errors and increased track loss. I have tried to explain our research to you, and I'm waiting for your questions. Thank you for listening to me.
Okay, thank you very much, Mr. Mustafa Kucuk, for giving us nice presentation. Now we open for the Q&A session. For all participants who have question, please raise your hand or type question on chat book. Okay, while we are waiting for participant to raise their question, Mr. Mustafa, I would like to ask you. So I just curious. So
Pak Imam, I'm sorry. I think he is left the Zoom due to some issue with our Zoom.
oh, okay.
So I think could we collect the question and then we will send them to the Mustafa Kucuk
Okay, that's good.
and let him answer that
Okay.
through email.
Okay.
Okay.
So I guess in this parallel session, I mean, that was the last presentation in this parallel session. And once again, I would like to thank to all speakers, to distinguished speakers, and to all participants for joining us today in this parallel session. Thank you very much. Once again, please continue to the next parallel session. Okay. See you. Bye-bye. Assalamualaikum.
Recording stopped. Recording in progress. Recording stopped. Recording in progress.
Everyone. Sorry for the late because I need to find out how to put myself in the room one. Yeah. So now we are going to listen to the talks of 5 presenters. I am Johnny Wellman Simatupang. I came from President University. Will be the session chair of this of the session 10 about electronics, material components, and circuits. Yeah, thank you for the existence. All of us here from Siska Ilhami, Prima Rusliani, Rizky Dewa Berlian, Unik Nurhayati, and Vinay Kumar. Okay, there will be 5 presenters. Now we will start. from the first presenter by Siska Ilhami with the paper with performance analysis of graphene oxide coated QCM sensors for humidity detection. Yeah, you will have about 10 minutes presentation and then continue by the Q&A. If anyone would like to ask something, you can ask by raise your hand or typing the question on the chat box. Okay, let's start from the first presenter, Siska Ilhami from IPB University. Time is yours.
Thank you for the time and opportunity. Assalamualaikum warahmatullahi wabarakatuh. It is an honor for me to present to you our work entitled Performance Analysis of Graphene Oxide Coated QCM Sensor for Humidity Detection in International Conference on Radar and Microwave Electronic and Telecommunication, or ICRAMET 2024. Okay, jump to the first presentation, which is the introduction. Humidity is a measure of the water vapor content in the air, which play an important role in areas such as agriculture, electronic, and healthcare. Because of this, humidity sensors are very important. However, there are still many problems encountered when using humidity sensors, such as slow response, low sensitivity, and high cost. Quartz crystal microbalance or QCM sensors have gained considerable attention for their simple design, affordability, high sensitivity, sub-nanogram precision, and quick response. One of the key factors in QCM sensor performance is the sensing layer material used. In this research, graphene oxide or GO material is used because it has various oxygen functional groups on its surface. These groups make GO highly hydrophilic, enabling it to effectively absorb water molecules. This study aimed to evaluate the performance of a humidity sensor based on QCM coated with GO. The study investigated the sensor sensitivity, hysteresis, response, and recovery time with varying GO layer thicknesses resulting from different drop numbers. A QCM sensor consists of quartz crystal placed between two electrodes and operates based on the piezoelectric properties of quartz. When a voltage is applied, it induces a resonant frequency, and any additional mass on the crystal surface reduces this frequency, enabling precise mass measurement. The Sorber equation governs the relationship between the add mass and the resulting change in frequency. When water molecules are adsorbed onto the GO surface, the mass change occurs on the quartz crystal, leading to the shift in frequency. This frequency shift is monitored as the sensor responds to varying humidity levels. Methodology. The first, synthesis of graphene oxide using the modified Hammers method with graphite as the precursor and potassium permanganate as the oxidizer. Then deposition of GO on the QCM surface using the drop casting technique and varying the drop number. And then the sensor performance were tested across humidity levels ranging from 40% to 90%. Result and discussion. First, analyze the diffraction pattern to identify the success of GO synthesis that has been carried out. This result showed an increase in dispacing after the oxidation process from 0.33 to 0.84 nanometers, which is caused by the addition of oxygen functional group between the graphene layers, so that the layers become more separated, indicating the success of geosynthesis. And then the surface morphology of the GO layer deposit on the QCM electrode. The geo surface appears flat and uniform with fine wrinkles typical of geosid. The physical properties, including surface area and porosity, were assessed using the BET method with results summarized in this table. Next, we analyze the oxygen-containing functional group using FTIR spectroscopy. This figure displays several peaks that indicate oxygen-containing groups on the geosurface, including hydroxyl, carboxyl, and alkoxy groups. QCMs are well known for their high sensitivity to change in surface mass. When GO suspension was applied to the QCM sensors, a linear relationship appeared between the decrease in vibration frequency of the quartz crystal and the mass of material A. This table shows that there is an increase in the frequency shift and mass of GO on the QCM sensor as more solution is deposited on its surface, in accordance with the survey equation. Next, we test the sensor performance in detecting humidity. Sensitivity is the critical factor in assessing the performance of QCM humidity sensors. In this research, the sensitivity of the QCM humidity sensor was determined by the calculating the ratio of the resonant frequency shift to change in relative humidity. As shown in figure, the frequency shift of the GO called QCM sensor increased with rising humidity levels. This research showed that GO2 exhibit the highest sensitivity with moderate mass loading. This is because moderate mass loading can offer an ideal balance between sufficient absorption, material, and film thickness that allow efficient diffusion and access to active site, leading to higher sensitivity. In addition, the relationship between frequency shift and relative humidity is not linear. However, in the relative humidity range of 40% to 90%, all samples show a logarithmic increase in frequency shift. Humidity hysteresis refers to the maximum discrepancy between the absorption and desorption response curve at the same relative humidity point. This figure presents the humidity hysteresis characteristic of the sensors as they move through the relative humidity range of 40% to 90% and back. It is evident that each sensor nearly returns to its baseline frequency, with the humidity hysteresis reaching its highest point at elevated humidity levels for all sensors. Significantly, the amount of GO deposit on the QCMs influence its moisture hysteresis behavior, with higher GO amount resulting in more significant hysteresis. The maximum humidity hysteresis for GO1, GO2, and GO3 occurs at around 85% relative humidity. And then test the response and recovery time. Testing these parameters help determine how quickly the sensor can react to change in humidity and return to its baseline after the change. In the study, the GO2 sensor was selected for further testing due to its excellent humidity sensitivity. As shown in the figure, the QCM sensor with a GO coating exhibited a response time of around 77 seconds and a recovery time of approximately 16 seconds. The study showed that the sensors tend to have a longer response time compared to the recovery time. This is because at higher humidity levels, the physical absorption of water molecules takes longer to reach equilibrium, resulting in a longer response time. Conclusion: this study examined the effectiveness of graphene oxide layers as sensing material in QCM-based humidity sensors. The QCM sensor showed the linear relationship between mass loading and frequency response. However, sensitivity analysis indicated the higher sensitivity didn't correspond to the most significant mass loading. In particular, the GO2 sensor with the medium mass loading exhibit the higher sensitivity, achieving 91.06 Hz per percent relative humidity. This highlight that finding the optimal balance between material amount and film thickness is crucial for maximizing sensor sensitivity. Additionally, the GO2 sensor demonstrates a response time of 77 seconds and the recovery time is 16 seconds. Overall, this research emphasized optimizing mass loading and better understanding material properties to improve QCM-based humidity sensor performance. Okay, thank you for your attention. Wassalam.
Thank you, Ms. Siska Ilhami, for the good presentation. Is there any question or comment from the audience, from the floor? Please, if there is any question. Okay, thank you for Mr. Bani Muhammad, PhD, asking about what is the current technologies response time, and is it yours comparable? Please, Ms. Siska, maybe you can address the question. I unmute your microphone. Hello, Ms. Siska? Are you hearing me? Do you hear me? Sorry, there is no voice from your side.
Hello.
Yes, it is okay. Yeah.
Okay.
Yeah.
Okay, thank you for the question. The current response time
According to your knowledge, what is the current technology's response time? And is it comparable with yours?
the response times in the sensor is comparable because the response times of the sensor is I think the sensor have quickly respond. Sorry, the response time is measured using the same method in as frequency shift measurement. Only this use a certain amount of time.
Is there any other question from the floor?
Sorry?
No, I mean, is there any other question from the floor? No, maybe I would like to ask one question, Ms. Siska. It's a simple question about, so did you make your own sensors here, or the commercial one?
The QCM sensor is commercial.
But then you use graphene oxide coated on the top of the QCM.
Yes.
So you bought the commercial one, then you you modified some next
graphene
modification. Yeah, okay.
yeah. Yes.
Okay, thank you. Okay. If there is no other question, I think we can conclude this session. For the Mrs. Ilhami, we give applause for her presentation. Thank you.
Thank you.
Okay, maybe we can continue with the second presenter, which is Mr. or Miss ya, Prisma Rusliani. Miss Prima Rusliani from ITB. A promising passivation strategy using hydroxyl cellulose for enhancing the performance in organic-based perovskite solar cells. Please, the time is yours for the presentation, and then we will.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Prima Fitri Rusliani. I'm a master student from Physics Engineering, Bandung Institute of Technology. The title of the manuscript that I submit to ICRAMET 2024 is a promising passivation strategy using hydroxyethyl cellulose for enhancing the performance of inorganic-based perovskite solar cells. My supervisor is Professor Brian Yulerto, PhD, and the co-supervisor is Professor Natalita Maulani Nursan, PhD. The co-author of this manuscript are shown in the slide. The outline of these presentations are introduction, experimental section, results and discussion, conclusion that include the future work of this research. The introduction or the background of the research is about inorganic perovskite solar cells such as cesium lead bromide, cesium lead iodide, or cesium lead chloride has their own characteristic, such as wide band gap, high stability under the ambient condition, resistance to the high temperatures and to degradation in the air, and high environmental tolerance. Besides of the merits of the materials, there are the demerits, especially for cesium lead bromide solar cells. Inhomogeneity of perovskite layer that can caused by the interfacial defects. With the typical defects like this is like light vacancies, iodide vacancies, interstitial or substitutions. These interfacial defects can decrease the open circuit voltage and increase the device degradation. And this defect can make a charge carrier lost and decreasing the perovskite solar cells performance. To overcome this problem, we introduced interfacial engineering that involves the incorporation additives designed to form the chemical bonding between dissolved free ions from the perovskite layer while simultaneously reducing the trap densities. And from interfacial engineering, we can enhance the perovskite film quality and mitigate energy level mismatch. And after overcome the defect problem, the photocarrier recombination can be expressed. One of the materials of the additives or pacivators is AGC or hydroxyethyl cellulose. AGC is a derivative cellulose which non-toxic natural polymers and can be a promising pacivators for enhancing the interaction between the hydroxyl groups of the cellulose and the free ions in the perovskite film. And this is the experimental section that I made. I made perovskite solar cell with this configuration that I use FTO substrate, titanium dioxide as an electron transport materials for both compact and mesoporous, cesium lead bromide as perovskite materials, AGC as a pacivators, and carbon as an electrode. The schematic image of perovskite solar cell fabrication process are shown in the middle figure. That I prepared a FTO substrate and then compare a mesoporous titanium dioxide deposition. And then I made two variations in this research. There are shown with the red and blue arrow. Red arrow represent the fabrication flow or before samples, that is AGC layer, deposit before perovskite layer. And then the blue arrow represents the fabrication flow for AGC layer, deposit after perovskite layer. And then after this, I made the perovskite layer with a multi-step deposition. The last step is carbon electrode deposition with Dr. blade. And then in this research, I made 3 samples with control, that is no AGC, before samples, that is AGC, deposit before perovskite layer, and after samples, that AGC, deposit after perovskite layer. And the materials that I used here, shown in the figure, and a characterization that I use are UV spectroscopy, FTIR, photoluminescence, JV characteristic using sun simulator, and EIS or electrochemical impedance spectroscopy. The first results is absorbance spectrum that I get from UV spectroscopy measurement. That is from the graph we can see the black line represents the control, the red line represents the before samples, and the blue line represents the after samples. The after samples has the higher absorbance intensity that exhibit quantity of the extracted charge that directly influence the magnitude of generated current. So from this result, we can see that after sample can result the higher current density than the control one. The onset of this absorption approximately at 500 nanometers, and from this data we can generate with dot plot to find the band gap. From all these samples, the AGC modification have a lower band gap than this control one, even though the variation is very small. And the FTIR spectra from control and after samples are shown in the figure. There is no big difference because the AGC layer that is deposit on or after perovskite layer is too thin, so the detector cannot detect the AGC layer. The FTIR spectra can show the transmitted intensity of the after sample is lower than the control one, that is correlate with the absorption spectrum before. And then the photoluminescence spectrum, we can see the after sample has a lowest peak than the others. And the lowest peak is indicating the low non-radiative recombination. And if we see, there is a small shifting to the shorter wavelength that's called blue shift. To investigate the effect of AGC to the perovskite solar cells performance, we measure the JV curve using the sun simulator AM 1.5 G filter, and this is the results. Detailed performance of solar cells are shown in the table 1. The control samples can reach the power conversion efficiency 1.27% with the open circuit voltage 0.94 volt, and the AGC modification before and after can increase the power conversion efficiency to 2.09% and 3.06% with the higher another performance parameters. And this result can support by the EIS measurement, electrochemical impedance spectroscopy, which study the charge transport dynamic in the dark condition with the bias voltage 0 volt. And in the Fit-Nyquist plot, there is one semicircle that corresponds to the recombination resistance. And the detail of the resistance of the solar cells are shown in the table 2. Rs is the series resistance and Rx is the recombination resistance. And the after samples has the highest recombination resistance with 590 kilo ohm. From these results, there is suggesting that the passivation process is effectively can suppress the carrier recombination with hydroxy at the cellulose addition. So the conclusion of this research are incorporation of AGC, effective the absorbance properties, and then the modified and improved accelerated photocarrier transport with the low recombination, and the optimized device achieve significantly improved the open circuit voltage and the power conversion efficiency to 3.06%. And the future work of this research are varying the AGC concentration and conducting further characterization to confirm the AGC as a pacifier in the perovskite solar cells. This is my presentation. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Prima, for the next presentation. Is there any question from the floor about this topic? Any question? Maybe you can also check in the chat box. Here's my question. I will ask a question maybe. You mentioned about the promising passivation strategy using HAC for enhancing the performance. So, we compare also this strategy with other strategy in sprint.
I'm sorry, I cannot catch your question.
Oh,
can you repeat your question?
I think your Mr. Johnny Simatupang voice is a little bit
low, very low.
Yeah.
Is it okay now? Is it okay now?
Okay.
Is it okay? Okay. So, have you compared your strategy with other strategy also?
I just compare the use of AGC, the AGC materials in the cesium lead bromide peroxide materials. I don't make a comparison with another materials, but I use AGC because of in the previous work and the other paper that use AGC in the different perovskite materials such as methyl ammonium lead iodide.
Can you mention again one of the benefits?
One of the benefits of AGC.
Of your strategy. I mean, you mentioned about enhancing the quality, the film quality, thin film quality, something like that, right?
Yeah. In this manuscript, I don't show the SEM or the further characterization to confirm or to validate that AGC can enhance the morphology or the film of perovskite. But from the absorbance measurement or the parameters photovoltaic measurement, AGC can increase the quality of the device perovskite seismically bromide. Maybe for the we need the further characterization.
Okay, thanks. Yeah, thank you for the answer. Yeah.
Thank you.
Okay, thank you for the presentation, and we give applause to Ms. Prima Rusliani for the nice presentation and discussion. Let's continue with the third presenter, Miss Rizky Deva Berlian. Performance of PVA SNO2 and PVA ZNO as sensing materials for thick film resistive type humidity sensors. The time is yours, and then we will continue with the Q&A.
Good morning, everyone. I am Rizky Deva Berlian from the Department of Physics at IPB University, and today I will be presenting our study on performance of polyphenol alcohol tin dioxide and polyphenol alcohol zinc oxide as sensing materials for thick film resistive type humidity sensors. This research is a collaboration between IPB University, Research Center for Electronics, and University Technology Malaysia. The table of content are introduction, experimental method, result and discussion, and conclusion. The first is introduction. The measurements of humidity is crucial in various fields such as agriculture, pharmacy, chemistry, and etc. Resistive type humidity sensors are widely used due to their high sensitivity, low cost, and easy of operation. The sensors operate on the principle of water vapor absorption, where water vapor absorption leads to the formation of ionic hydroxyl, so it can reducing resistance and increasing conductivity. The sensors are often made by using thick film technology, which is screen printing techniques, and the sensors has sensitive layers, can include polymers and semiconductor metal oxides. In the study, we are using polyphenol alcohol or PVA as polymer, which is PVA is a biocompatible and water-soluble polymer, so it is a promising polymer, but it has high resistance value. So to enhance the PVA-based sensor, we have added metal oxide like tin dioxide and zinc oxide to improve conductivity. And the study focused on using nano-sized tin dioxide and zinc oxide with PVA to better humidity detection. Next is experimental methods. The first is resistive type humidity sensor structure. The structure of resistive type humidity sensors are an aluminum substrate, an interdigital electrode, and in the study we are using silver palladium paste, and then the electric layer and the sensing layers. Humidity sensors were fabricated with two different designs, which are 6 pairs, and we call it with F6, and 8 pairs, and we call it with F8 of interdigital electrodes, with the dimension as shown is on the figure. The second is synthesis of tin dioxide and zinc oxide nanoparticles. We are for make tin dioxide nanoparticles, we are using hydrothermal method within tetrachloride pentahydrate as precursor. And to make zinc oxide nanoparticles, we are using sol gel method with zinc acetate dihydrate as a precursor. And the synthesis steps as shown on the screen. The third is polymer metal preparation. Its solution was prepared by dissolving PVA plus SNO2 and PVA plus ZNO into the ionized water and stir it for 6 hours at 90 degrees Celsius. Afterward, let the solution cool down, then mix with ammonium persulfate and stir again for 30 minutes. The The fourth is electrical characteristic measurements. To analyze the sensor electrical characteristics, we conduct tests in a control chamber setup. The receive humidity sensor was tested at room temperature with a 5-volt and 2 milliampere supplied by Ketley high resistance meter. Humidity levels inside the chamber were varied from 60% relative humidity to 90% relative humidity using by humidifier. Next, result and discussion. The first is result of nanoparticles. From the test, we are known that SNO2 nanoparticles showing a tetragonal structure with average particle size distribution measurements result of 8.9 nanometers. And zinc oxide nanoparticles have an hexagonal structure with an average size distribution 11.8 nanometers. This indicates that the synthesized materials is nanostructures. Nanostructures materials have a high surface area to volume ratio, so it can enhancing performance by increasing interaction between active sites and water molecules. Second is electrical characterization result. Based on the graph, it is known that by adding metal oxide nanoparticles to PVA can enhance conductivity by increasing active sites for water interaction. So it can reducing sensor resistance. From the graph 2, we can also know that sensor F8 has a lower initial resistance than F6. Why? It is due to its larger surface area can providing more active sites to absorb water vapor and enhancing conductivity. Next is the thickness of sensitive layers. The thickness of sensitive layers can be affect to the performance of humidity sensors. From PVA SNO2 nanoparticles based sensors, the thinnest sensitive layer is owned by F8 with 5% SNO2, which is 40.12 micrometers, and the thickest is owned by F8 with 10% SNO2, which is 53.4 micrometers. Meanwhile, PVA ZNO nanoparticle based sensors has the thinnest sensitive layer is owned by F6 with 5% ZNO, which is 5.1 micrometers, and the thickest is owned by F8 with 10% ZNO, which is 128.3 micrometers. The next is response and recovery time. For PVA SNO2 based sensor with 10% SNO2 has a faster response time than the PVA with 5% SNO2 humidity sensors. It can also known that by addition of SNO2 and sensor layer thickness can impact sensor response time. With more SNO2 generally accelerating it. It is such as PVA with 10% SNO2. But in PVA ZNO-based sensor, ZNO 5% are more faster than 10% because 10% has a too thick sensitive layer, such as in PVA with 10% ZNO on humidity sensor. It can reduce responsiveness at low humidity levels, so it takes a longer time. And from the graph 2, we can see that PVA ZNO-based sensors have difficulty returning to their original state after detecting humidity. Why? This is due to the zinc oxides has a hygroscopic nature and porous microstructure. Next is sensor sensitivity. The sensitivity of humidity sensors can be calculated from the ratio of the change in resistance to the change in percent relative humidity. From the graph 2, the alteration in metal oxide mass concentration and the number of electrodes influence the sensitivity of the humidity sensors. Last is conclusion, but in the study, it can conclude that screen printing with thick film technology is effective for fabricating resistive type humidity sensors. PVA zinc oxide sensors showing lower resistance, but PVA tin dioxide showed better linearity and consistency of response. And sensors with a larger surface area tend to produce lower resistance values. And polymer metal oxide can lowering the resistance humidity sensors without reducing its water vapor absorption ability. That's all from me. Thank you so much for your attention. Good morning.
Yeah, thank you for the great presentation from Ms. Rizky Deva Berlian. Yeah, there is a question here from Pak Robert Manurung. Yeah, the main problem with humidity sensors is long-term stability, which means the sensor's performance can degrade over time, especially when exposed to high humidity. So the question is, have you evaluated this matter in your sensor performance, Ms. Rizky? This sensor is also affected by environmental such as temperature. What is the optimum working temperature in your sensor, for your sensor? Two questions. Please address the question.
Okay, thank you for the question. By the sensor that we are fabricate, we are using at room temperature. Why? Because this at room temperature, our sensor can optimum working, which is 25 degrees Celsius.
25 degrees Celsius, the working temperature of your sensor?
Or at room temperature.
Yeah, of your sensor, yeah?
Yes.
Okay. So this is the best performance, yeah, in your sensor, for your sensor.
Yes. I think for the sensor we are fabricated at room temperature have optimum working temperature.
Is there any degrading over time when you use the sensor for, let's say, a few days along your experiment?
What can you repeat? Sorry.
Is there any degrading over time after you using your sensor few days?
I think it can.
So is it okay? Still okay?
Yeah.
Oh, okay. Okay, thank you, Pak Robert, for the question. Can I ask a simple question? Do you have the picture of tetragonal and hexagonal of your results?
Yes.
Yes.
We have.
Oh,
but
so
yeah, we enter to the
the paper. Oh, okay.
Because our focus is not on the structure picture, yes, but for the performance of the sensor.
Okay. So this is this is micrometer and nanometer technology.
Yes.
Okay. Okay. Then thank you for Ms. Rizky. We give applause for the presentation and discussion.
Thank you so much.
Okay, thank you. Now we continue with the fourth presenter, Ms. Nunik Nurhayati from BRIN, Electron Lifetime, Electron Transport Time Determination device with PTPW 11CS cellulose composite as counter electrode in dye synthesized solar cell DSSC. The time is yours.
My name is Nunik Nurhayati. I will present our research study with the title Electron Lifetime and Electron Transport Time Determination of the Device with PTPW11CS cellulose as a counter electrode in dye-sensitized solar cells. And here is the outline of my presentation. I will start from the introduction. The SSC is photovoltaic cell that converts solar energy into electrical current using organic and inorganic material as light harvester. The SSC is a third generation of solar cells, introduced by Oregon and Gretzel in 1991 as a low-cost photovoltaic cell. But the SSC consists of a photoanode, dye, electrolyte, and counter electrode. Here is the work diagram of the SSCs. Now we are focusing on electrolyte time, charge transfer, and recombination. Electrolyte time is the average time an electron remains in the conduction band of the semiconductor before recombining with a hole. So we can say that electrolyte time is how long an electron can stay in the band. Electron transport time is the time required for electron to transit from the conduction band of the IO2 to the external circuit. And electron recombination is electron falls back into dye or electrolyte. Electrolyte time, electron transport time, and electron recombination are important in determining performance of the SSCs. Thus, focusing of this study is to determine electrolyte time and electron transport time by transient photovoltaic and transient photocurrent measurements. For the experimental, it starts from device fabrication. Photoanode was sandwiched with counter electrode one to another, then dropped by the electrolyte solution. Counter electrode consists of FTO, platinum, and PW11CS mixed with cellulose as a binding material. And as a control, PW11CS doesn't exist on the counter electrode. PW11CS is a polyoxometallate or denoted as POMS derivative. It is anionic metal oxide clusters. Characteristics of POMS are high stability, easy to synthesize, high catalytic activity, and high redox states. This is why POMS can be utilized as a doping material in the SSCs, whether as a photoanode, an electrolyte, or a counter electrode. And here is some examples of POM utilizations in the SSCs. And for the characterization, we conducted IV measurements, transient photovoltaic and transient photocurrent measurements using a suitable slow modulation frequency with a square modulated technique and light intensity dependent of IV measurement. And the time for result and discussion. The figure shows the IV curves of the SSC devices with PW11CS as counter electrode and its control, or without PW11CS. Several parameters of IV characteristics are obtained, such as the power conversion efficiency, open circuit voltage, short circuit current density, and fill factor, as shown in the table below. The device with PW invensi S shows JAC value higher than its control. As the effect of increasing of JAC value, the power conversion efficiency of the device with PW invensi S is also increasing compared to its control. The increase in JAC possibly resulted from a decrease in electron recombination. To explore electron recombination, transient photovoltaic measurement with a square modulated was conducted. These measurements provide information about electron lifetime, which is correlated with electron recombination. Light intensity dependence of CPV measurements were conducted on the device with PW invensi S and its control. These figures show normalized photovoltaic versus time as light intensity dependence for the device with PW invensi S and its control, respectively. Electron lifetime data are extracted from these graphs using double exponential fitting as shown in Table 2 and visualized in Figure 3. Electron lifetime data can provide information about recombination. As shown in Table 2, there are two electron lifetime data obtained from each measurement. Tau E1 is noted as fast recombination and Tau E2 is noted as slow recombination of the electron. Fast recombination refers to recombination to homodie. However, slow recombination refers to recombination to electrolyte. From the graph, it can be seen that the device with PW invensi S has Tau E1 and Tau E2 longer than its control. In the SSC, electron recombination can be determined by electron lifetime, in which, by the increasing of electron lifetime, electron recombination is decreasing. On the other hand, the JAC value will be enhanced if electron recombination decreases. Thus, this can explain why the JAC value of the device with PW invensi S is higher than its control due to the decreasing of electron recombination. From the graph of Figure 3, it can also be seen that by increasing the light intensity, electron lifetime for both devices are decreasing. This means that the electron recombination process is dependent on light intensity. Now we move to transient photocurrent measurement. Figure 4 shows normalized photocurrent versus time with light intensity dependence for devices with PW invensi S and its control. Transport time data are extracted from Figure 4 using double exponential fitting. Extracted data are shown in Table 3 and visualized in Figure 5. As shown in Table 3, there are two transport time data obtained from each measurement. Tau TR1, which is noted as fast electron transport, and Tau TR2, which is noted as slow electron transport. Fast electron transport refers to electron injection into the conduction band of TiO2, whereas slow electron transport refers to electron transport in TiO2 to an external circuit. The device with PW invensi S has electron transport time faster than its control, which leads to the enhancement of JAC. This indicates that the device with PW invensi S performs better than its control. Figure 5 also visualizes light intensity dependence, in which electron transport time is decreasing by the increasing light intensity. It means that the electron transport time of the device with PW invensi S and its control are light intensity dependent. Let's move to light intensity dependence IV measurements. These measurements were conducted to reveal the effect of light intensity on IV characteristic parameters. Figure 6 shows the IV curves of the device with PW invensi S as a function of light intensity. IV parameters such as efficiency, VOC, JAC, and FF are extracted from Figure 6. Extracted data are shown in Table 4 and visualized in Figure 7. By increasing light intensity, efficiency, and JAC are increasing. However, VOC and FF are not influenced significantly by the increasing light intensity. And for the conclusion, in this work, we study about electron lifetime and electron transport time of the device with PW11CS as counter electrode and its control through transient photovoltaic and photocurrent measurement. TPV measurements show that the device with PW11CS as a counter electrode has electron lifetime longer than its control, indicating a slow recombination process and enhancing JAC. TPC measurements show that the device with PW11CS as a counter electrode has electron transport time faster than its control, which leads to enhancement of JAC. Both measurements indicate better performance of the device with PW11CS as shown by the enhancement in power conversion efficiency, electron lifetime, electron transport time, and some electrical parameters of IV of the devices are light intensity dependent. And the last, the authors express our gratitude to RIM LPDP BRIN for funding the research and to all the supporters in these research activities. Thank you.
Thank you for the nice presentation from Miss Nuni Nurhayati. Yeah. Okay. Is there any question or comments from the floor for this presentation? Any comment or question? No? Okay. Maybe I'll ask question, yeah? Ms. Nuni. Just a simple question. How did you measure the lifetime and transport lifetime in your experimental method?
Yeah, actually, I measured the electron light. Okay, thank you for the question, Mr. Johnny. And actually, I measured the electron light time and electron transport time with the square modulated technique using with the method TPV and TPC. TPV, transient photovoltaic measurement. From transient photovoltaic measurement, we can determine electron lifetime, and from TPC, transient photocurrent measurement, we can explore electron transport time. So the technique is a square modulated technique, and in here we get the graph. From the graph, we elaborate the data. We extract the data using double exponential fitting. So from the double exponential fitting, we can get the electron lifetime data or electron transport time data.
Oh, so it is not directly from the facility, yeah?
Oh no, not directly. We have to fitting the data. We have to fit the data. Yeah, yeah. With some with some double exponential fitting.
So is it in microsecond or nanosecond?
Actually, let me check it first. So it is in microsecond.
Microsecond.
Microsecond, yes.
Okay.
Millisecond. Sorry, millisecond.
Milli. Oh, milli.
Yeah, millisecond. Yeah, this is for the SSC. The SSC usually longer than perovskite solar cell. Usually perovskite solar cell, it should be nano or micro, but in the SSC is
milli.
Yeah, in milli, slower.
Slower.
Yeah.
Any other question from the floor? No? Okay. Then thank you for Ms. Nuni Nurhayati for the great presentation and discussion. Okay. We give applause.
Okay. Thank you.
Thank you. Last but not least, there will be the fifth presenter from Vinay Kumar, PES University, India. Hardware implementation of systolic array architecture using 4:2 compressor approximate multiplier for image processing operations. You have 15 minutes. The time is yours.
Good morning to one of our present here. I'm very much delighted to be presenting our work in this conference, and I thank all the dignitaries here for this opportunity. I'm Vinay Kumarian, a final year MTech student, along with my co-author, Mr. Suman Sakrasar, an assistant professor who has been a great support for me in this research. Both are from the Department of Electronics and Communication Engineering at PES University, Bangalore, India. I'm here today to present our work titled Hardware Implementation of Systolic Array Architecture using 4:2 compressor approximate multiplier for image processing applications. Our project focuses on efficient edge detection by comparing two systolic array architecture, one integrated with exact multiplier and the other one with the data approximate multiplier, which uses 4:2 compressor. So this comparison demonstrates how optimized delay and area characteristics can enhance the speed and resource efficiency critical for real-time image processing applications. So these are the list of contents that I'll be walking you all through. Let's start with the introduction to systolic array architecture. The term systolic is derived from the medical field, integrated with its synchronous and rhythmic contraction of a human heart in transferring blood supply to all parts of the human body. Similarly, in computational field, a systolic architecture operates to allow the flow of data in synchronized and pipeline manner. So this is achieved with the help of its sophisticatedly organized interconnected grids of processing element that contains MAC unit in its core, which I'll be talking about it later. So this approach achieves high speed and low latency computation and are efficient for matrix multiplication or operations, which are commonly used in image processing, signal processing, and neural network applications, and so on. So the processing elements in our architecture are designed to receive the data from two directions, that is top and the left, as you all can see in slide, which gets computed, then passed on to then pass the results to the adjacent processing element. This continuous flow enables each element to contribute to the computation and until the resultant output is yielded at the bottom, leading to the faster processing time. So the set can also be achieved by placing the weights in the processing element and feeding the stream of inputs from the left as input for computation. So you all can see the flow of data in here, where the input is being is being transported to the processing element, and there it gets multiplied with the current weight, and then gets transported to the adjacent processing element, there where there they get summed up with the latest produced product. So this is carried throughout the architecture and yielding the resultant matrix element at the bottom end, where you all can see YA1, YA12 are the resultant matrix elements. So this is the basic flow of systolic architecture in general. This is the block diagram of the processing element, where it contains a multiplier, adder, a register. Here, matrix A input and the matrix B input are appended onto the multiplier, where it gets multiplied. The product is being transported to the adder, where it gets summed up with the previous processing element's output, and the sum is being stored in the register until it gets transported to the subsequent processing element. This is the proposed processing element where the dada multiplier is being placed instead of the exact multiplier. We can configure it with whatever multiplier that we want. This is the block diagram of exact multiplier, where two input or two 8-bit inputs is being multiplied, and they generate partial products which been added and finally yielding the final product. This is the block diagram of dada multiplier, where two 8-bit inputs have been multiplied and resulting in the generation of partial products, and these partial products are being reduced with the help of compressors, and finally adding and yielding the final product. So these are the partial product that is being generated by multiplying two 8-bit inputs. So these partial products are being reduced with the help of compressors, as I said earlier, and finally resulting in the final products. So because of this compressors, the reduction stage is here only 3. If it weren't for this compressor, the reduction stage would have been 5 or 6. So, so talking about the hmm, approximation technique. The approximation technique here that we have used is in the approximation region, the least significant carry bit are being completely neglected, and in the exact region, every bit is being considered for the computation. So this is done so to have a balance between the faster processing time and the minimal with the minimal accuracy loss. The objective of our project was to implement 8 cross 8 data approximate multiplier in the PE, which using which we implemented 128 cross 128 systolic architecture, and finally comparing the results and the results of performance of proposed architecture and the architecture with the exact multiplier. Coming to the literature survey, various studies have examined multiplier architecture, approximate computation method, and systolic architecture to improve power consumption, area reduction, resource efficiency, and delay. Some research explores the advantage of different multipliers, while other focus on multipliers like a dual quality 4:2 compressor and exact and inexact computation in the systolic architecture that saves up the power and area significantly. Further studies investigate techniques like zero clock gating, bus invert coding, and other paper like LUT based methods for faster data processing are also observed. So in summary, the data and the Wallace tree multipliers are efficient for the application tolerant to minor accuracy loss, with our study prioritizing the data approximate multiplier in its for its simplicity and performance. So this is the methodology that we are following. Our system begins by converting inputs input images pixel into hexadecimal values, and these hexadecimal values are being converted into matrix matrix format using with the help of row buffer encoder and decoder after the output is yielded, and then gets converted back to the hexa pixels no which is used for reconstruction of the image. So this is the row buffer architecture that I was talking about. Here, the row buffer architecture consists of 3 row buffers, which is being complemented by 3 FIFOs, where the input of the converted values, that is hexa values, are being transported to this row buffers. So 128 values will be populating the row buffer, and then it phases the next 128 values will be stored in this row buffer 2, similarly in row buffer 3. So after the the values been populating this row buffer, the first 3 elements of the 3 row buffers will be realized as the this is the elements that I was talking about. The first 3 elements of the row buffers will be realized as the input matrix, which will be sent to the architecture that will be computed, and the resultant will be will be moved on. So the while the processing is being done, the next 3 elements will be populating the gap that is being created. So, and then the first 3 again elements will be realized as the input, and this flow will be continuing until the last elements, last 3 elements will be that will be sent into the architecture for the computation. Similarly, the opposite will be done in the decoder side, where the the output that we'll be getting will be placing here, and then subsequent output will be placing in the vacant gaps that will be in the decoder side. So like the last matrix will be computed and will be yeah, after it gets stored here, this is converted back to the pixel values, helping in the reconstruction of the image. So this is the kernel matrix. For the kernel matrix, we are using 3x3 Laplacian filter. So this second order derivative filter identifies region of rapid intensity change, effectively detecting edges in all direction, unlike directional filters like Sobel or perfect filter. So this makes it ideal for capturing edge across various orientation. With the systolic architecture performing the necessary computation. So these are the simulation results that we have got. This is the simulation result of exact multiplier. So x and y are the inputs, and result is the result of the the product of this inputs. This is the simulation result of the Dada multiplier, where A and B are the result. Inputs, and product is the result. In this exact multiplier, there is no accuracy loss. There's precise product. And here we can find a bit of accuracy loss, and the accuracy loss can be found here in the error part. So we will have this accuracy issue due to the approximation method that we are following. This is a simulation result of the systolic architecture that is being used, that has the integration of exact multiplier. Here these are the kernel values, the Laplacian filter, and this systolic data 1, 2, 3 are the systolic, processing hexadecimal values of the image. Similarly, these are the simulation result of the systolic actors that integrates Dada multiplier. Here again, this is the systolic, processing data of the pixel values of the image here. So the comparison, so our results show that Dada approximate multiplier integrates the systolic array, systolic architecture, outperforming the architecture that with the exact multiplier design by achieving 21.24% reduction in area and 56.95% faster processing and 23.67% lesser LUTs and 34.78% lesser reduction in the flip-flop usage. So this gains highlight the approximation multiplier balances the performance and efficiency, making it well suited for real-time applications like edge detection, where speed and power savings are essential. So these are the edge detection outputs. So to evaluate and the effectiveness of our design, we applied our systolic architecture to perform edge detection on various test images. The results showed almost accurate edge mapping. Here, the parameters such as SSMI, PSNR, and MSE, that is mean square error, can be witnessed, demonstrating that despite the approximation, our design provides a reliable output for image processing task. So in conclusion, using approximation multiplier in systolic architecture significantly enhances resource efficiency, speed, and power consumption, making it ideal for embedded and real-time processing, image processing applications. Further direction includes dynamic approximation to adapt accuracy based on the task needed, and expanding to the advanced applications like feature extraction, object recognition, highlighting the broader potential for the approximation multiplier in the computer vision. These are the references papers that I have taken for our projects, and this is the plagiarism report that I have obtained for my paper in the college. Thank you all for the attention.
Then thank you, Mr. Vinay Kumar, for the good presentation. Yeah, and all information inside. Any question from the floor or any comments from anybody here for the presentation? Okay. Let me ask some question, Mr. Vinay Kumar.
Yes, sir. Yes.
What simulation software did you use?
Sir?
What is the simulation software you use?
I'm sorry, I didn't get you. What simulation?
What is the simulation software you use?
Software.
Yeah.
Sir, I used Xilinx Vivado software, sir, for the simulations and all, and Model Sim.
Oh,
software.
okay. So you build the environment by yourself
Yes, sir.
and also including the parameters.
Yes.
So what is the size of your matrix?
Sir, the systolic matrix is 120. I mean, the input matrix is 128 cross 188, but the processing that I'll be doing, the computation, that will be in 3 cross 3 matrix, sir.
Okay. What about the power? I saw in your slide number 31.
No, it's 333.
Yeah. I mean the slide number 31.
Yeah.
Yeah, you
So,
saw in the slide. Yeah. Why is the power is not really different between the existing architecture and the proposed architecture?
sir, in the existing architecture, due to the large number of partial products that is being generated, due to the computation of all that, the power is more. And here, no, the large number of compressors to compress the partial products. Due to that, the power is more. So in the power parameter, both are almost similar, but in terms of area and delay, I was able to optimize it better using this approach, proposed architecture.
So you mean you optimize the usage of power, although you increase the what's called the data you use. I mean, if we can go back to the slide number 31.
Sure. Can I share?
Yeah, maybe you can share for a while.
Yes.
Yeah. I just wondering with your you share the slide number 31. Slide number 31. Yeah. Here. Yes. You keep the power here almost the same, yeah.
Sir, I wasn't, as I said, I wasn't able to tweak between the power. The processing time, the processing power with the both architecture, it remained the same despite of many trial and errors that I did. But apart from the power, I was able to reduce the area and the delay, sir. That's what I said.
So I'm just asking, you keep the power, or the power is
No, the power that is using by the architecture. That is the output. I didn't do it.
So is it so this is the benefit, the advantage of your.
No, this is actually a con, I can say, in this particular architecture. The power is a bit more, but the advantage of this is the proposed architecture by mine is the reduction in the area and the reduction in the delay.
Okay.
So there is a trade-off between in the architectures existing and the proposed.
Okay. Yeah. Thank you, Mr. Vinay.
Thank you, sir.
Yeah. We give applause to Mr. Vinay Kumar. Yeah. And very good presentation and discussion.
Thank you so much, sir. Thank you, everybody.
Okay. For all, thank you for your presentation. We hope we can see you again in the next ICRAMET 2025 next year. Yeah. That's for me. Thank you for all and see you again. You can go back to the meeting room.
How can you design the perfect car before driving a single mile? How do you construct a building that redefines a city before building anything yourself? How can you develop world-changing tech without changing your timeline? The answer is simulation. Physics-based simulation generates insights at every step of product development, allowing your creations to get certified, compliant, and on the market sooner. This means you can build a virtual cruise ship and see how it fares on the open sea. Erect a full-scale virtual twin of a factory and make certain it will be operational in real life. Construct the ideal commercial aircraft and ensure it can withstand the elements. With simulation, no matter what you dream up, it will be enhanced with data, insight, and most of all, revelation. Simulia, reveal the world we live in.
So Simulia is the dedicated simulation brand from Dassault Systems. It enables designers and engineers to physically validate their designs in a virtual environment, and that can accelerate innovation and it can save time and money by reducing physical prototypes. So Simulia covers a wide spectrum of different engineering disciplines, from structures and multi-body systems to fluids, electromagnetics, and vibroacoustics. It's also got powerful automation and optimization technology that underpins all of those disciplines, which really allows analysts to make the best engineering decisions in the development and the validation of their products. The Simulia solutions are available both as standalone desktop applications and within the cloud-based 3D Experience platform. The same underlying technology is used by both, but the 3D Experience platform offers tighter integration of the Simulia solutions and the rest of the Dassault Systems portfolio. So the SOLIDWORKS simulation solutions are actually very good for many different simulation problems. But when you start to simulate more complicated physics, you may find that you hit the limitations of what SOLIDWORKS can do. That's where Simulia comes in. So Simulia has a wide breadth of capability and it can do things which SOLIDWORKS simulation simply can't do. It can also do things which SOLIDWORKS can do, but do it a lot better in terms of accuracy, in terms of speed, and in terms of reliability. Simulia also has a larger R&D resource than what SOLIDWORKS simulation has. So with Simulia, you can be confident that you'll always benefit from the latest advancements in simulation technology. Some of the greatest benefits of 3D Experience Simulia stem from the 3D Experience platform itself and its tight integration with the Dassault Systems portfolio. It allows users to collaborate easily and provides a consistent user experience across the Simulia solutions, irrespective of the type of simulation you're working on. The cloud-based nature of the 3D Experience platform also means that you can run your simulations in the high-performance cloud compute infrastructure, meaning that you can run the most complex simulations on even a basic laptop. Given how much capability there is within the Simulia solutions, there can be quite an awful lot to learn. With that said, there are dedicated training courses for each of the Simulia solutions, and that's available both in a classroom and through an online learning portal. And for every new Simulia user, we'd look to provide a degree of onboarding to help with their successful adoption of the software. There are a few different options available when it comes to licensing for Simulia. Most people will opt for a quarterly or an annual subscription, but it is also possible to access a perpetual license of some of the Simulia solutions. When it comes to cloud compute on the 3D Experience platform, many of the roles include this at no additional cost to some extent, but if you want to fully unlock the power of the cloud, you'll need to purchase additional credits and tokens. The most well-known Simulia solution is probably Abacus, which is the dedicated structural finite element analysis package. But other key solutions include XFlow and PowerFlow, which operate under the fluids domain, CST Studio Suite and Opera under electromagnetics, Wave 6 under vibroacoustics, and SimPack under multibody.
Railway System, or LRS, is a subsidiary of PT Land Industry Persero, which has been established since 2012 to fulfill various needs in railway sector, with long experience in railway sector for almost 30 years. LRS becomes a market leader in E&M railway sector in Indonesia, including products, engineering, and services. In a regional market, LRS has been acknowledged as a strategic partner to develop turnkey E&M system and perform multinational partnership in turnkey E&M system field, both for light rail and heavy rail. LRS acquired both national and regional large-scale projects according to its great work and experiences. As to prove our commitment in reaching our vision and mission, LRS products such as SealSafe 4000 and SealTrack LS 3000 has been certified by Ministry of Industry for domestic component level. LRS has been certified by the International Engineering Certification through ERCE, Certified Professional Engineering PII, and Company Certification ISO 9001, ISO 14001, and OHSAS 80001. LRS the most reliable world-class partner for railway system and turnkey light rail E&M system. And our mission is to contribute improving people productivity and mobility through delivering reliable and safe railway system. We are land railway system with innovation, engineering, services, and partnership with delivery safety and capacity.
Research is our strength to overcome any limitations. Innovation is the guiding vision that drives us towards the future. We cannot face this alone. We must stand together to make our vision a reality. Growing strong upon the land of Nusantara, a magical place filled with miracle and wonder. A land spanning 2 continents and 2 oceans, rich in culture and biodiversity. We and Indonesia are the necessary combination to realize the grand visions of the future. Like an orchestra, BRIN harmonizes research, development, assessment, application, and also synergies, invention, and innovation in Indonesia. We created an ecosystem consisting of 7 deputies, 12 research organizations, and 85 research centers dispersed throughout Indonesia. Research Organization for Aeronautics and Space, Research Organization for Nuclear Energy, Research Organization for Energy and Manufacture, Research Organization for Earth Sciences and Maritime, Research Organization for Life Sciences and Environment, Research Organization for Electronics and Informatics, Research Organization for Social Sciences and Humanities, Research Organization for Archaeology, Language, and Literature, Research Organization for Health, Research Organization for Nanotechnology and Material, Research Organization for Agriculture and Food, Research Organization for Governance, Economy, and Community Welfare. BRIN catalyzing research and innovation to develop an advanced scientific ecosystem in Indonesia with 2 main targets. BRIN realizes the tremendous potential of the nation's youth in the field of science and technology. Thus, various research and innovation policies are being formulated to develop and cultivate human resources with high competence and aptitude in science and technology. Creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized through the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or RIDA. Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums. BRIN organizes research into a more effective and efficient process by integrating human resources, infrastructure, and budget from various research and development institutions. Oriented by a national research priority, BRIN routinely enacts comprehensive evaluations from various research and development institutions. This effort is supported through the continued management and improvement of various research and innovation facilities located across 17 regions of Indonesia, dedicated towards the development of science and technology. BRIN continues to improve our contribution to research and innovation towards national development by developing and revitalizing 4 areas of science and technology, or KST. An integrated area consisting of research laboratory facilities, testing laboratories, and industrial facilities for both startups and SMEs, tenant office rooms, co-working space, meeting rooms, gallery rooms, and other supporting facilities. BRIN is here to manifest.
JET is a journal published by Pusat Penelitian Elektronika dan Telekomunikasi LIPI. JET presents high-quality articles on the latest research and development in the field of electronics, telecommunication, and micro or nanoelectronics engineering. JET provides a platform to share research in the areas such as digital signal and image processing, network theory and circuit design, radar and sonar technology, antenna and wave propagation, wireless and optical communication, microelectronic system, electromagnetic and electronics materials, emerging and advanced fabrication technology, and so on. JET is indexed by internationally renowned indexers such as DOAJ, Google Scholar, Mendeley, and etc. JET is also ranked as Center 2 in Kemenristek BRIN accreditation system. There are 2 JET editions published every year, and all of them are available in open access to support global exchange of knowledge. All submissions in JET are accepted online, and each submission will be blindly reviewed by at least 2 peer reviewers. Most importantly, all submissions are free of charge, and therefore, no article processing fee applies. For more info, please visit www.journalet.com or visit our social media accounts.
Cultivate human resources with high competence and aptitude in science and technology, creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized through the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or RIDA. Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums. BRIN organizes research into a more effective and efficient process by integrating human resources, infrastructure, and budget from various research and development institutions. Oriented by a national research priority, BRIN routinely enacts comprehensive evaluations from various research and development institutions. This effort is supported through the continued management and improvement of various research and innovation facilities located across 17 regions of Indonesia, dedicated towards the development of science and technology. BRIN continues to improve our contribution to research and innovation towards national development by developing and revitalizing 4 areas of science and technology, or KST. An integrated area consisting of research laboratory facilities, testing laboratories, and industrial facilities for both startups and SMEs, tenant office rooms, co-working space, meeting rooms, gallery rooms, and other supporting facilities. BRIN is here to manifest the future of a golden Indonesia 2045 by consolidating science and technology resources and creating a resource ecosystem and research-based economical foundation. Transforming Indonesia as a global reference in the development and application of science and technology, practices, and the good of humankind. Nature is the source of inspiration. Knowledge is the foundation, and to be put in praxis for the sake of the nation.
How can you design the perfect car before driving a single mile? How do you construct a building that redefines a city before building anything yourself? How can you develop world-changing tech without changing your timeline? The answer is simulation. Physics-based simulation generates insights at every step of product development, allowing your creations to get certified, compliant, and on the market sooner. This means you can build a virtual cruise ship and see how it fares on the open sea. Erect a full-scale virtual twin of a factory and make certain it will be operational in real life. Construct the ideal commercial aircraft and ensure it can withstand the elements. With simulation, no matter what you dream up, it will be enhanced with data, insight, and most of all, revelation. Simulia, reveal the world we live in.
So Simulia is the dedicated simulation brand from Dassault Systems. It enables designers and engineers to physically validate their designs in a virtual environment, and that can accelerate innovation and it can save time and money by reducing physical prototypes. So Simulia covers a wide spectrum of different engineering disciplines, from structures and multi-body systems to fluids, electromagnetics, and vibroacoustics. It's also got powerful automation and optimization technology that underpins all of those disciplines, which really allows analysts to make the best engineering decisions in the development and the validation of their products. The Simulia solutions are available both as standalone desktop applications and within the cloud-based 3D Experience platform. The same underlying technology is used by both, but the 3D Experience platform offers tighter integration of the Simulia solutions and the rest of the Dassault Systems portfolio. So the SOLIDWORKS simulation solutions are actually very good for many different simulation problems. But when you start to simulate more complicated physics, you may find that you hit the limitations of what SOLIDWORKS can do. That's where Simulia comes in. So Simulia has a wide breadth of capability and it can do things which SOLIDWORKS simulation simply can't do. It can also do things which SOLIDWORKS can do, but do it a lot better in terms of accuracy, in terms of speed, and in terms of reliability. Simulia also has a larger R&D resource than what SOLIDWORKS simulation has. So with Simulia, you can be confident that you'll always benefit from the latest advancements in simulation technology. Some of the greatest benefits of 3D Experience Simulia stem from the 3D Experience platform itself and its tight integration with the Dassault Systems portfolio. It allows users to collaborate easily and provides a consistent user experience across the Simulia solutions, irrespective of the type of simulation you're working on. The cloud-based nature of the 3D Experience platform also means that you can run your simulations in the high-performance cloud compute infrastructure, meaning that you can run the most complex simulations on even a basic laptop. Given how much capability there is within the Simulia solutions, there can be quite an awful lot to learn. With that said, there are dedicated training courses for each of the Simulia solutions, and that's available both in a classroom and through an online learning portal. And for every new Simulia user, we'd look to provide a degree of onboarding to help with their successful adoption of the software. There are a few different options available when it comes to licensing for Simulia. Most people will opt for a quarterly or an annual subscription, but it is also possible to access a perpetual license of some of the Simulia solutions. When it comes to cloud compute on the 3D Experience platform, many of the roles include this at no additional cost to some extent, but if you want to fully unlock the power of the cloud, you'll need to purchase additional credits and tokens. The most well-known Simulia solution is probably Abacus, which is the dedicated structural finite element analysis package. But other key solutions include XFlow and PowerFlow, which operate under the fluids domain, CST Studio Suite and Opera under electromagnetics, Wave 6 under vibroacoustics, and SimPack under multibody.
Land Railway System, or LRS, is a subsidiary of PT Land Industry Persero, which has been established since 2012 to fulfill various needs in railway sector, with long experience in railway sector for almost 30 years. LRS becomes a market leader in E&M railway sector in Indonesia, including products, engineering, and services. In a regional market, LRS has been acknowledged as a strategic partner to develop turnkey E&M system and perform multinational partnership in turnkey E&M system field, both for light rail and heavy rail. LRS acquire both national and regional large-scale projects according to its great work and experiences. As to prove our commitment in reaching our vision and mission, LRS products such as SealSafe 4000 and SealTrack LS3000 has been certified by Ministry of Industry for domestic component level. LRS has been certified by the International Engineering Certification through ERCE, Certified Professional Engineering PII, and Company Certification ISO 9001, ISO 14001, and OHSAS 80001. LRS the most reliable world-class partner for railway system and turnkey light rail E&M system. And our mission is to contribute improving people productivity and mobility through delivering reliable and safe railway system. We are land railway system with innovation, engineering, services, and partnership with delivery safety and capacity. Jurnal Elektronika dan Telekomunikasi or JET is a journal published by Pusat Penelitian Elektronika dan Telekomunikasi LIPI. JET presents high-quality articles on the latest research and development in the field of electronics, telecommunication, and micro or nanoelectronics engineering. JET provides a platform to share research in the areas such as digital signal and image processing, network theory and circuit design, radar and sonar technology, antenna and wave propagation, wireless and optical communication, microelectronic system, electromagnetic and electronics materials, emerging and advanced fabrication technology, and so on. JET is indexed by internationally renowned indexers such as DOAJ, Google Scholar, Mendeley, and etc. JET is also ranked as Center 2 in Tentang BRIN accreditation system. There are 2 JET editions published every year, and all of them are available in open access to support global exchange of knowledge. All submissions in JET are accepted online, and each submission will be blindly reviewed by at least 2 peer reviewers. Most importantly, all submissions are free of charge and therefore no article processing fee applies. For more info, please visit www.journalet.com or visit our social media accounts.
Research is our strength to overcome any limitations. Innovation is the guiding vision that drives us towards the future. We cannot face this alone. We must stand together to make our vision a reality. Growing strong upon the land of Nusantara, a magical place filled with miracle and wonder. A land spanning 2 continents and 2 oceans, rich in culture and biodiversity. We and Indonesia are the necessary combination to realize the grand visions of the future. Like an orchestra, BRIN harmonizes research, development, assessment, application, and also synergies, invention, and innovation in Indonesia. We created an ecosystem consisting of 7 deputies, 12 research organizations, and 85 research centers dispersed throughout Indonesia. Research Organization for Aeronautics and Space, Research Organization for Nuclear Energy, Research Organization for Energy and Manufacture, Research Organization for Earth Sciences and Maritime, Research Organization for Life Sciences and Environment, Research Organization for Electronics and Informatics, Research Organization for Social Sciences and Humanities, Research Organization for Archaeology, Language, and Literature, Research Organization for Health, Research Organization for Nanotechnology and Material, Research Organization for Agriculture and Food, Research Organization for Governance, Economy, and Community Welfare. BRIN catalyzing research and innovation to develop an advanced scientific ecosystem in Indonesia with 2 main targets. BRIN realizes the tremendous potential of the nation's youth in the field of science and technology. Thus, various research and innovation policies are being formulated to develop and cultivate human resources with high competence and aptitude in science and technology. Creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized through the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or RIDA. Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums. BRIN organizes research into a more effective and efficient process by integrating human resources, infrastructure, and budget from various research and development institutions. Oriented by a national research priority, BRIN routinely enacts comprehensive evaluations from various research and development institutions. This effort is supported through the continued management and improvement of various research and innovation facilities located across 17 regions of Indonesia, dedicated towards the development of science and technology. BRIN continues to improve our contribution to research and innovation towards national development by developing and revitalizing 4 areas of science and technology, or KST. An integrated area consisting of research laboratory facilities, testing laboratories, and industrial facilities for both startups and SMEs, tenant office rooms, co-working space, meeting rooms, gallery rooms, and other supporting facilities. BRIN is here to manifest the future of a golden Indonesia 2045 by consolidating science and technology resources and creating a resource ecosystem and research-based economical foundation. Transforming Indonesia as a global reference in the development and application of science and technology practices and the good of humankind. Nature is the source of inspiration. Knowledge is the foundation, and to be put in praxis for the sake of the nation.
How can you design the perfect car, before driving a single mile? How do you construct a building that redefines a city before building anything yourself? How can you develop world-changing tech without changing your timeline? The answer is simulation. Physics-based simulation generates insights at every step of product development, allowing your creations to get certified, compliant, and on the market sooner. This means you can build a virtual cruise ship and see how it fares on the open sea. Erect a full-scale virtual twin of a factory and make certain it will be operational in real life. Construct the ideal commercial aircraft and ensure it can withstand the elements. With simulation, no matter what you dream up, it will be enhanced with data, insight, and most of all, revelation. Simulia, reveal the world we live in.
So Simulia is the dedicated simulation brand from Dassault Systems. It enables designers and engineers to physically validate their designs in a virtual environment, and that can accelerate innovation and it can save time and money by reducing physical prototypes. So Simulia covers a wide spectrum of different engineering disciplines, from structures and multi-body systems to fluids, electromagnetics, and vibroacoustics. It's also got powerful automation and optimization technology that underpins all of those disciplines, which really allows analysts to make the best engineering decisions in the development and the validation of their products. The Simulia solutions are available both as standalone desktop applications and within the cloud-based 3D Experience platform. The same underlying technology is used by both, but the 3D Experience platform offers tighter integration of the Simulia solutions and the rest of the Dassault Systems portfolio. So the SOLIDWORKS simulation solutions are actually very good for many different simulation problems. But when you start to simulate more complicated physics, you may find that you hit the limitations of what SOLIDWORKS can do. That's where Simulia comes in. So Simulia has a wide breadth of capability and it can do things which SOLIDWORKS simulation simply can't do. It can also do things which SOLIDWORKS can do, but do it a lot better in terms of accuracy, in terms of speed, and in terms of reliability. Simulia also has a larger R&D resource than what SOLIDWORKS simulation has. So with Simulia, you can be confident that you'll always benefit from the latest advancements in simulation technology. Some of the greatest benefits of 3D Experience Simulia stem from the 3D Experience platform itself and its tight integration with the Dassault Systems portfolio. It allows users to collaborate easily and provides a consistent user experience across the Simulia solutions, irrespective of the type of simulation you're working on. The cloud-based nature of the 3D Experience platform also means that you can run your simulations in the high-performance cloud compute infrastructure, meaning that you can run the most complex simulations on even a basic laptop. Given how much capability there is within the Simulia solutions, there can be quite an awful lot to learn. With that said, there are dedicated training courses for each of the Simulia solutions, and that's available both in a classroom and through an online learning portal. And for every new Simulia user, we'd look to provide a degree of onboarding to help with their successful adoption of the software. There are a few different options available when it comes to licensing for Simulia. Most people will opt for a quarterly or an annual subscription, but it is also possible to access a perpetual license of some of the Simulia solutions. When it comes to cloud compute on the 3D Experience platform, many of the roles include this at no additional cost to some extent, but if you want to fully unlock the power of the cloud, you'll need to purchase additional credits and tokens. The most well-known Simulia solution is probably Abacus, which is the dedicated structural finite element analysis package. But other key solutions include XFlow and PowerFlow, which operate under the fluids domain, CST Studio Suite and Opera under electromagnetics, Wave 6 under vibroacoustics, and SimPack under multibody.
Land railway system, or LRS, is a subsidiary of PT Land Industry Persero, which has been established since 2012 to fulfill various needs in railway sector, with long experience in railway sector for almost 30 years. LRS becomes a market leader in E&M railway sector in Indonesia, including products, engineering, and services. In a regional market, LRS has been acknowledged as a strategic partner to develop turnkey E&M system and perform multinational partnership in turnkey E&M system field, both for light rail and heavy rail. LRS acquire both national and regional large-scale projects according to its great work and experiences. As to prove our commitment in reaching our vision and mission, LRS products such as SealSafe 4000 and SealTrack LS 3000 has been certified by Ministry of Industry for domestic component level. LRS has been certified by the International Engineering Certification through ERCE, Certified Professional Engineering PII, and Company Certification ISO 9001, ISO 14001, and OHSAS 80001. LRS the most reliable world-class partner for railway system and turnkey light rail E&M system. And our mission is to contribute improving people productivity and mobility through delivering reliable and safe railway system. We are land railway system with innovation, engineering, services, and partnership with delivery safety and capacity. Jurnal Elektronika dan Telekomunikasi or JET is a journal published by Pusat Penelitian Elektronika dan Telekomunikasi LIPI. JET presents high-quality articles on the latest research and development in the field of electronics, telecommunication, and micro or nanoelectronics engineering. JET provides a platform to share research in the areas such as digital signal and image processing, network theory and circuit design, radar and sonar technology, antenna and wave propagation, wireless and optical communication, microelectronic system, electromagnetic and electronics materials, emerging and advanced fabrication technology, and so on. JET is indexed by internationally renowned indexers such as DOAJ, Google Scholar, Mendeley, and etc. JET is also ranked as Center 2 in Kemendristek BRIN accreditation system. There are 2 JET editions published every year, and all of them are available in open access to support global exchange of knowledge. All submissions in JET are accepted online, and each submission will be blindly reviewed by at least 2 peer reviewers. Most importantly, all submissions are free of charge, and therefore, no article processing fee applies. For more info, please visit www.journalet.com or visit our social media accounts.
Research is our strength to overcome any limitations. Innovation is the guiding vision that drives us towards the future. We cannot face this alone. We must stand together to make our vision.
Recording in progress.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Welcome to the parallel session 14, Antenna Device and Techniques of the International Conference on Radar, Antenna, Microwave Electronics, and Telecommunications. My name is Johannes Galiodioga from Research Center for Telecommunication BRIN, and I will be serving you as your moderator for this session. In this session, we have 5 papers that will be presented through pre-recorded video. And after each video presentation, we will proceed with the live Q&A with the respective authors. And before we start the presentation, I would like to confirm that all speakers are already in this room. I will call each speaker's name, and if you could, please respond to confirm your presence. And for the first paper will be presented by Mr. Aditya Inzani Mahdiat. Are you there, Mr. Adit?
Yes, I'm here.
Okay, thank you. And the second paper will be presented by Mr. Raden Priyo Aji. Are you with us?
Yes, I'm here.
Okay, thank you. And the third paper will be presented by Mrs. Tri Ratnasari, are you with us?
Yes, I'm here.
Okay, thank you. And the fourth paper will be presented by Mr. Masum Verma. Are you with that? Mr. Masum Verma, are you there? He is not in the participants box. Yeah, I think he will be join us. And for the last paper will be presented by Mrs. Nazik Hussein Ibrahim. Are you with us? Mrs. Nazik Hussein Ibrahim or Mr. Ahmed Jamil Abdul Qadir?
Yes, I'm here.
Okay,
Behalf
thank you.
of my supervisor, dear Ahmed Jamil.
Okay, I see. Okay, thank you for confirming. And for the guidelines, each speaker will have about 10 minutes to deliver their presentation. And once all presentations are completed, we will have a Q&A session for a maximum of 5 minutes. And I strongly recommend you ask the question with English. And please use the raise hand feature or write down your question in the chat box. And now we will begin with our first presenter. I invite Mr. Aditya Inzani Wahyudiyat from University of Indonesia and Research Center for Electronics BRIN to deliver your presentation about performance comparison of 2x2 MIMO antenna with meta-surface structure for mitigating mutual coupling in 5G MIMO system. Mr. Aditya, the screen is yours.
Hello everyone, thanks for joining me today. My name is Aditya Inzani Wahyudiyat and I'm here to discuss my work on enhancing the performance of 2x2 MIMO antennas by using metasurface structures to mitigate mutual coupling, specifically within 5G MIMO systems. This presentation will explore how metasurface integration could help solve one of the critical challenges in MIMO technologies, which is managing mutual coupling. To give you an overview of today's presentation, here's the agenda. I will explain the motivation and challenges of this research, continue it with unit cell design, and then 2x2 MIMO antenna configuration, results and analysis, and conclusions. 5G, the fifth generation of wireless technologies, offers significant improvements over previous generations, including faster data speed, lower latency, and greater reliability. This enables a fast increase in connected devices and enhanced overall network capacity. A key technology behind 5G capabilities is MIMO, or multiple input, multiple output, which uses multiple antennas to transmit and receive signals. MIMO has proven to significantly boost data rate. As we can see in the picture on the right, adding more antennas to the system increased the data rate achievable at the same signal-to-noise ratio value. But multiple antenna system in MIMO configuration have disadvantages. It's very susceptible to mutual coupling due to the close physical spacing between antennas. This coupling affects the antennas during both transmission and receptions, leading to reduced antenna gain, increased noise level, and higher error rate. As a result, this factor can significantly degrade performance in 5G systems. The value of mutual coupling has a direct impact on the symbol error rate, or SER. Specifically, as mutual coupling increases, the symbol error rate also rises. Therefore, it is crucial to lower the mutual coupling value to enhance the overall performance of MIMO system in 5G application. In recent years, metasurface have gained popularity in various electromagnetic applications due to their ability to manipulate electromagnetic waves upon interaction with their structures. In this research, we will explore the potential of metasurface to reduce mutual coupling in MIMO antenna systems. Additionally, the development of VLS EBG, or electromagnetic bandgap structures, allow for smaller unit cells, enabling antennas to be placed much closer together without sacrificing the antenna size. In this research, we will compare several metasurface structures placed between the MIMO antennas. Our goal is to achieve mutual coupling reduction without sacrificing the distance between antennas, allowing for a more compact antenna systems. The method we use to design the unit cells involves analyzing the dispersion diagram. High impedance structures such as EBG exhibit unique dispersion relations when designed with periodic patterns. By analyzing the dispersion relation, we can identify the frequency range where a band gap occurs. This information is essential for understanding how the metasurface can effectively mitigate mutual coupling. Calculating periodic structures become less effective when we design structures with too many variations, too many unit cells. This complexity can lead to increased computational demands and longer simulation times. By employing block theorems, we recognize that waves in periodic structures exhibit the same symmetry and periodicity as their host material. Therefore, by calculating just only the unit cells and applying periodic boundaries conditions, we can achieve results equivalent to those obtained from simulating multiple unit cells. This slide illustrates an example of periodic boundary condition applied in CST software. By simulating just one unit cell, we effectively model an infinite array of unit cells, allowing us to analyze the periodic structure's behavior without the computational burden of simulating each unit cell individually. This is the dispersion diagram for two types of common unit cells, a rectangular patch unit cell and a mushroom type unit cell, which feature a sorting pin to the ground. In the mushroom type design, we observe that the resonance of the first mode is shifted to the lower frequency. Additionally, there is a band gap occur between the first and second modes, indicating a frequency range where propagating waves are not allowed. By using the mushroom type design, we can effectively miniaturize the size of unit cell. However, the implementation of the sorting pin presents challenges during fabrication process, which must be carefully addressed to ensure optimal performance. Our research presents three types of unit cell inspired by Amanda line designs. These unit cells have the ability to shift resonance frequencies to lower values without the need for a sorting pin. Notably, the type C unit cells is the particularly compact, the small one, yet it resonates at the lower frequency compared to the other designs. By carefully optimizing the dimension of these unit cells, we can achieve a resonance frequency of 3.5 GHz for each types. To evaluate the characteristic of mutual coupling at 3.5 GHz in the MIMO antenna, with metasurface between it, we vary the distance between the antennas while the unit cell was placed in between. This approach allows us to assess how the metasurface influences mutual coupling as the antenna spacing changes. Placing an array of unit cells between the MIMO antennas has proven effective in reducing mutual coupling. However, the design of the unit cells also influences the optimal separation distance between the 2x2 MIMO antennas. Although the unit cell design exhibits similar dispersion characteristics, their shapes enable optimal mutual coupling reduction at different antenna separation distance. Specifically, design C achieve optimal mutual coupling reduction at 1.06 lambda 0, design B at 1.61 lambda 0, and design A at 2.86 lambda 0. Overall, the configuration has mutual coupling value lower than antenna without metasurface. Here we can observe the result of S parameter for the antenna integrated with type A unit cells. The mutual coupling represented by S21 has been successfully reduced by incorporating a metasurface between the radiators. Notably, the S parameter for input reflection, or S11, remains below -10 dB across all three types of metasurface configuration, indicating that the performance of the antenna is preserved, the resonance of S11, while reducing the mutual coupling. And this is the type B. As we can see, it has still have the same resonance of S11, but the mutual coupling is reduced a lot. And this is the type C. By analyzing the mutual coupling results, we can conclude that MIMO system is less likely to experience performance degradation. The effective reduction in mutual coupling enhances the overall reliability and efficiency of the 5G systems. Another way to assess MIMO performance is by examining the envelope correlation coefficient, or ECC, and the diversity gain. These metrics provide valuable insight into how effectively the MIMO system is. We observe that all unit cells, all types exhibit an envelope correlation coefficient, or ECC, below 0.05 at 3.5 GHz, indicating minimal correlation between the antenna elements. Additionally, the diversity gain approaches 1 at all types, suggesting that the system effectively leverages multiple antennas to enhance the performance of the system. This research demonstrates that metasurface structures can significantly reduce mutual coupling in MIMO systems. The analysis of dispersion diagrams simplifies the design process for metasurface unit cells by enabling the calculation of resonance propagating wave along the structures. Moreover, we can miniaturize the unit cell using a Manderline-like design. For instance, in design C, the unit cell is reduced to just 0.91 lambda null. The shape and size of the unit cells play a crucial role in optimizing the design for mutual coupling reduction. In summary, design A, B, and C achieve mutual coupling reduction of 40 dB at separation distance of 2.860 lambda null, 30 dB at 1.61 lambda null, and 13 dB reduction of mutual coupling at 1.06 lambda null, respectively. Thank you for your attention for today.
Okay, thank you, Mr. Aditya, for your presentation. Now we start the Q&A session. Is there any question? You can raise your hand or write down the question in the chat box. Question? Okay, if there's no question from the audience, I just want to ask a simple question, Mr. Aditya. I want to know the effect of the antenna spacing in the metasurface structure. Is there any upper or lower limitation in case of distance? You can answer it.
Okay, so the distance of the metasurface unit cell, you mean?
Yeah.
Yeah, the gap between the unit cell will affect the, well, actually, the gap between the unit cell will affect the resonance frequency, actually. And also, if you put it into like an EBG something, the bandwidth also changing. So the gap of the metasurface is changing the characteristic of the resonance frequency, both bandwidth and the resonance, actually.
Okay. Okay. Thank you, Mr. Aditya. Okay, is there any question? In the chat box, Mr. Johnny asked about what is exactly the meaning of metasurface in your research?
Yeah, this one. So the meaning of metasurface in my research is the unit cell will have a different properties when it's placed in periodically structures. You know, when it puts in like 5 array or 6 array or in periodic configuration, the properties of the unit cell will be changing. You see that the resonance of the dispersion diagram is changed.
Yeah, metal is like material, yeah, metamaterial, metasurface, yeah.
Yes, yeah.
Thank you, Mr. Johnny and Mr. Aditya. And one question again from Mr. Teguh, please, Mr. Teguh Praludy.
Okay, thank you, Mr. Moderator, Mas Gali, and I will ask to Mr. Aditya Injani. Mas Adit, I want to ask you about different design unit cell for the metasurface and the metamaterial with the DGS, diffratic ground. What is the different the design?
Oh.
Because in the DGS we make defect at the design. Thank you.
Usually the DGS is placed in the ground structure side, so it will be a slot configuration, not patch like mine. But usually, like a Babinet principle, the resonance frequency will be the same. Like you know the SRR and CSSR. The difference is one slot and one is patch, but the resonance is usually be the same.
Thank you, Mr.
Usually.
Adit.
Yeah.
Okay, thank you.
Okay, thank you. I think the time is limited, so thank again, Mr. Aditya, for your presentation and your answer.
Thank
And
you,
let's
Mr.
move.
Yans.
Let's move to the second presenter. The second presenter will be the Mr. Raden Priyo Aji from National Research and Innovation Agency Indonesia to deliver a presentation about low-cost 9.4 gigahertz microstrip patch antenna design with PLA and copper tape. So, Mr. Priyo, the screen is yours.
Good morning, everyone. Thank you for being here today. I'm excited to present our work with title Low-Cost 9.4 GHz Microstrip Patch Antenna with PLA and Copper Tape. I am as a presenter, Priyo Hartono Aji. I am working in Radio Frequency Microwave Acoustic Photonic Research Group from Research Center for Telecommunications, BRIN. In this project, we've aimed to create a cost-effective and eco-friendly antenna that maintains high performance using PLA and copper tape. Let's explore how this innovative design could impact radar, communication system, and sustainable technology. Thank you, and let's get started. I'm going to give a start with short description. We aim to provide an affordable, efficient solution for application in telecommunication, balancing performance with manufacturing simplicity and accessibility. And using of polylactic acid makes it compatible with 3D printing technology, enhancing its potential for scalable, low-cost production. And today's presentation gonna be there's introduction, requirement overview, and so on. I'm gonna start with introduction. The microstrip patch antenna, known for their compact planar design, widely used in modern communication system due to easy integration with other electronic device, especially the rise of the Internet of Things that every device is connected with each other. And secondly, there are traditional material common substrate like FR4, Rogers, Duroid, F4 BMX, such as offer good performance but are expensive and non-biodegradable, so raising concern about the cost itself and environment impact to the environment. So rising demand for sustainability, increasing round of researchers focusing on how to build the eco-friendly materials and biodegradable and could sustain with the global goals. So the research overview, it came to the focus. The background is one is microstrip antenna are vital in modern communication system. The secondly, the traditional substrate are costly and non-biodegradable. The third one is the need for eco-friendly, low-cost material for antenna production. So our mission is to explore and identify biodegradable material that can effectively replace traditional substrate for sustainability and also can without compromising performance in electronic and communication application. So we are offering solutions here a sustainable high performance alternative compared with the traditional substrate. We are using polylactic acid substrate as a filament in 3D printer for achieving the low cost and easy manufacturability. And the second one, for the structure itself, we are using copper tape, and we can manually apply on this on the substrate. It's forming for the radiation element. The third one is we are using copper tape also as a ground plane. We can find the copper tape in shopping merchant. So the requirement, we are as mentioned earlier, we need to build the 9.4 gigahertz that all mostly used in a radar system. Our approach is using the 3D printer who can easily manufacture. And our goals with the 3D printing approach is to create high performance, eco-friendly, rapid prototyping. If there's a problem, we can build another. So it will lead to the cost effective. So enabling customization for radar or wireless application. As I said earlier, PLA is biodegradable because it came from corn, who changing into starch, as we can see here in the life cycle of PLA. This is all became a PLA pellets and then become a 3D filament of PLA. And also it can easily decompose, but quite slow. As long as it can be decomposed in soil, it doesn't matter. So because this is the goals. So in the desired specification, as we can see before, we need to build the 9.4 gigahertz of center frequency. The patch form itself gonna be rectangular. The return loss, it's below or equal to minus 10 dB. Voltage standing wave ratio below or equal to. Impedance standard is plus minus 50 ohms. The substrate thickness 1.5 millimeters. We can build using the 3D printer to achieve that 1.5 millimeters. The substrate itself PLA, the patch and the ground it's copper tape with 50 microns thickness. So based on that center frequency, we came to the calculation and came to the standard equation. So as you can see here, to determine the width, we need only the speed of light divided by the 2 times center frequency and times the square root of the electric constant, resulting in the electric. As you can see here in the equation, the electric constant itself, it came from the measuring. First, we built the substrate and then put it in the center of the waveguide channel. Let's just say in here, we use the X-band. So there's some kind of formula to have the electric constant. But in here, we are just using what people already do. I mean the electric constant value, and then put it in here, so we can determine the width and length of the structure that we can build in the simulation. As you can see, and it also happen for the feed line width, feed line length, and the gap width. So based on above equation, gives us perspective to start doing simulation on CST Microwave Studio and build the antenna with the calculated device. So in based on that, we built the antenna in the simulation. As you can see here, the copper tape and also the PLA 3D filament, and the patch, it's on the top, on the ground plane, and at the bottoms. So based on the calculation, resulting this value. So I would like to mention the antenna design process overview for overall, but I'm gonna tell you about the in this project. Start, find reference for low-cost biodegradable material for substrate, and then measure the electric constant, as I said earlier, and then specify antenna requirement for design. Then they calculate width and length, and feed line width, feed line length, and so on. And then came to simulate design. And then if the decision process is result meet requirement, if there is no meet requirement, there gonna be optimization. And then finally, finalize the design for fabrication. So in the simulation, we can see here in the black in the black lines, as you can see, the unoptimized means that this one is a calculated value. As you can see here, the return loss of the unoptimized is only -8 dB. So based on this, we use a parameter sweep in the CSD Micro Studio for changing the weight, changing the length, and so on, for resulting the center frequency of 9.4 gigahertz as we desire. And then you can see here also the return loss is resulting as -17 dB. It's quite good. So our target it is achieved by and then the simulation, as you can see here, the bandwidth gain in radiation pattern is quite good, with approximately 7.11 dBi at 9.4 gigahertz, and the proposed antenna exhibit a directional radiation pattern with the main lobe directed perpendicular to the patch along the z-axis. The radiation pattern of this antenna reveals the E-plane has the magnitude of the 6.81 dBi, and for H-plane, its main lobe magnitude of 7.11 dBi with a side lobe level of -10.2 dB. So in here, as you can see, based on the return loss or input reflection coefficient, if we say input reflection coefficient, it means positive. So our target is achieved. So we came to the conclusion. We are also successfully designed and simulated 9.4 gigahertz microstrip patch antenna using PLA. And then we are achieving low cost, eco-friendly, and easily manufactured design. The antenna itself meets performance requirement for communication radar system and PLA, so potential as viable alternative to conventional substrate. The antenna performance is return loss -17 dB, and the bandwidth is 503 megahertz, and gain 7.11 dBi. Thank you. We're excited.
Okay, thank you very much, Mr. Tio, for your presentation. And now we'll begin the Q&A session. If there is question, you can raise your hand or write down your question in the chat box. Okay, maybe I will ask Mr. Priyo. Okay, I just want to know the method to get the permittivity, the dielectric constant, and the loss tangen for your PLA substrate. That's what.
Yeah, as you can see in my presentation, in that project, I just used the reference that people already did, and then see the value itself. But somehow we already fabricated, we already try and measure it, and how you use it before in your project as well. We are using the waveguide and put it, the substrate, the PLA substrate, put it in the center of the waveguide, the X-band waveguide. And then we measure there's some kind of formula to do that, but I'm not put it in the slides. Yeah, same standard for people who are doing in antenna design. Yeah.
Okay, thank you. Okay,
Welcome.
once more, thanks. I want to thank Mr. Pio and for your presentation, and then now we will go to the next presenter, and the third presenter will be Mrs. Sri Ratnasari from Institute Teknologi 10 November Indonesia to deliver your presentation about design of elliptical patch and half circular ground microstrip antenna with coplanar waveguide for chamber application. So, Mrs. Sri Ratnasari, the screen is yours.
Hello everyone, my name is Sri Ratnasari, and in this opportunity I would like to present our research paper with the title Design of Elliptical Patch and Half Circular Crown Microstrip Antenna with a Coplanar Waveguide Fitting for Chamber Application. Authors Mrs. Sri Ratnasari, Mr. Yon Hadi Pramono, Mr. Gatut Yudhoyono, and Mr. Suyatno from Institut Teknologi 10 November. The overview outline here of this presentation start by introduction and then design of the antenna, continue with the result and discussion, and the last is conclusion. Microstrip antenna are used in various applications, one of which is used to test the effectivity of wave-absorbing materials on the inner of the chamber. The chamber is designed to operate over a wide frequency range. Therefore, antenna with a wideband operating frequency are required. Recently, several techniques are applied to increasing the bandwidth, such as considering the size and the shape of the patch and the fitting. Elliptical patch antenna have received a lot of attention due to their wider bandwidth and the stable polarization. Meanwhile, the coplanar waveguide antenna is a type of the antenna where the patch and the crown are located on the same surface. So, it can reduce the radiation losses and increasing efficiency. Previous research. The antenna from figure 1 that proposed by Rahirja has operating frequency from 5.5 to 18 GHz. While in the figure 2, Srivastava, using a variation dimension slot inside of the elliptical patch, the antenna achieved a frequency range between 3.6 to 11.2 GHz. So, in this research, antenna is made with a wideband frequency at 1 to 18 GHz and has a size of 60 by 62 millimeters. Design of antenna. The first step is to analysis about the elliptical patch size. The lowest frequency parameter will be calculated to determine the reference dimension. We can calculate the elliptical patch size by the equation 1 until the equation 3. The next is analysis for fit line of coplanar waveguide antenna. The calculation of fit line impedance based on the following formula. We can see the fit line impedance calculate with equation 4 until equation 10. According to the formula for calculating the size of the patch antenna and the characteristic impedance, the value of parameter A, B, G, W, S, and the other is available in the table. The antenna has two designs that have difference in the crown shape. The antenna A has a rectangular crown, while the antenna B has a half circular crown. This difference is set at CG parameter. In the antenna A, CG parameter is 0, but in the antenna B, the optimization is carried out on the CG parameter, which has value of 10, 12, and 14. The next is the result of the return loss. The figure shows the simulation result graph for the antenna with a design. We can see that the antenna has a wide bandwidth in the frequency range of 1.85 to 9.92 GHz, and the return loss graph tends to show a fluctuating pattern at the certain frequencies. The figure shows that the comparison return loss value based on different CG parameter or curvature ground parameter in the antenna with B design. The optimization of parameter CG was conducted with value 10, 12, and 14, and the result of the optimization are shown in the table. From the table, we know that the maximum optimization is achieved by considering the bandwidth. So the antenna with CG parameter of 14 millimeters perform better than the others because it starts for a lower frequency and the return loss value for each minimum peak. The next is the result from the return loss. The figure shows that the comparison of return loss value for antenna with A design and the antenna with B design. Antenna with B design using CG value of 14 millimeters. At the frequency above 9 GHz, the return loss value of the antenna with A design is above minus 10 decibel, while the return loss of antenna with B design is below minus 10 decibel, so that the result achieves the wideband antenna target. The antenna use a half-circular crown, provide a less uniform distance between the patch and the crown, thus resulting in the wideband performance. Result in radiation pattern. The radiation pattern of the antenna is measured with an elevation angle at the theta of 0 degree and the frequency of 9.70 GHz. We can see in the figure 1, it shows about the radiation pattern from the antenna with a design. According to the result of this simulation, the major loop magnitude is minus 14.7 dBi, and the main loop direction is an angle of 90 degree, and the half power bandwidth is 89.80 degree. While in the figure 2 is in the antenna with B design, the antenna with B design result of the loop direction and half power bandwidth value of the antenna is same with the antenna A, while the value of the main loop magnitude is minus 13.6 dBi. Both of the antenna have a symmetrical radiation pattern, and the radiation direction is parallel to the antenna surface. The next is result in gain. We can see in the gain result at the frequency is calculating in the frequency 1 until 18 GHz, and both of the antenna has gain value range of 2.5 to 5 dBi. We can say that the antenna with B design has higher gain compared to the antenna with A design because the antenna with B design has average gain of 4.4 dBi, while antenna A has a gain value of 3.8 dBi. Conclusion: modify the rectangular crown antenna from design A into a half-circular crown antenna from design B has been successfully increasing the bandwidth. The optimization was performed on the ground curvature, and the best result was obtained at the value of 14 millimeters. The antenna works in the ring frequency of 1.81 to 18 gigahertz, and the maximum radiation is minus 13.6 dBi, and the gain average is 4.4 dBi. Thus, on the value of bandwidth and the radiation pattern, also the gain value, this antenna with be design is suitable for testing absorbing material in the chamber wall. Acknowledgement. This research was supported by Directorate General of Science and Technology Research and Higher Education through the scholarship master to doctoral education for excellent graduates. Maybe enough for my presentation, and thank you.
Okay, thank you, Mrs. Tri Ratnasari, for your presentation. And now I will open the Q&A session. Is there any question from the audience? Okay, this is one question in the chat box from Mrs. Masum Perma. Which optimization technique has been used for this work? Ms. Tri Ratnasari, please.
Okay, thank you for the question. It is a good question. Which optimization technique has been used for this work? For this optimization, we optimization about the CG parameter or the curvature ground parameter. It means that we modify about the upper corner of the ground, and it give a result. From my presentation, it so that the bandwidth is more wider. The CG parameter greatly affect the bandwidth of the antenna as shown in the simulation, and the antenna with CG value are use a half circular ground shape is to provide a less uniform distance between the patch and the ground, and it can increasing the distance affect the alternating electric field passes through the conductor.
Okay, is it enough, Mrs. Masum Perma? Okay. Yeah, I think it's enough, yeah. Okay, once again, I will thank you for your presentation, Mrs. Tri Ratnasari. And due to time constraint, let me move to another presentation. And in here we have 4 presenter for the session. I invite Mrs. Masum Verma from Indian Institute of Technology Madras to deliver a presentation about frustum-shaped conformal antenna array for air-to-ground communication. So, Mrs. Masum Verma, the screen is yours.
I'm going to present my work, frustum-shaped conformal array antenna for air-to-ground communication. So, modern A2G communication system in a surveillance system provide a raw data to achieve a comprehensive picture of surveillance area using multiple type of sensors. And also, they face the power and the weight constraint that limit their ability to perform data fusion on board. So in such cases, transmitting the collected data from multi-sensors using the high-capacity data link become essential. Designing antenna for A2G communication system also have several critical factors: beamforming, signal coverage, durability, etc. So by looking all these challenges, we are focused on primary 4 requirement. So it will start with the shallow angle gain. So shallow angle gain is requirement for the long range communication. Shallow angle are the angles which is close to the ventral field. And these are the elevation angle. And conventionally, the omnidirectional radiation pattern is required to cover all the azimuthal angle, and it's also provide the motion of the platform. So the third one is the lightweight, which is a requirement from the aerodynamics perspective. And the fourth, high gain bandwidth is requirement for sending that for making the high capacity data link. And for the last one, we have also proposed the sectoral design for the sectoral design, which are capable to cover the 360-degree azimuth. We start with our first problem. So the first challenge is coming from the aircraft body, which is act as a reflector and it will disturb the radiation pattern. So figure 1 is showing the geometrical and the coordinate of the understanding the nulls and the ripples, which is coming on a visible region. And the second figure is the normalized gain versus elevation angle, where the blue curve when the single antenna on the cylinder shape is radiate and maximum coming at a 90-degree. While keeping the same antenna under the PEC body, it will give the huge null. And for the third case, frustum shape, when we are giving the cone angle as a 15-degree, the null is getting less and it is also shifted. And after keeping the fourth plot is the frustum shape when the cone angle is a 30-degree. So the tilt in the angle, shifting the ripple and also minimizing it and pushing it out from the visible region. So from this analysis, it is quite clear the frustum shape is giving more freedom of degree to nullify the ripples in the elevation plane which will help in a shallow angle gain. So the next slide, that advantage is shown in the polar plot. So the third case not third case, in the polar plot, here we have plotted the cone angle of the 25 degree, and the nulls has been the reduction in the nulls can be very visible in the polar plot. So we will use this method, and by using this method, we have did the analysis and model the element design and whole frustum design. So we will start with the single radiating element design. So figure 3 is having the single element design, which is having, the design parameters are given into the caption of the figure, and the design will work from 4.4 gigahertz to 5 gigahertz, and the ABS material has been used for this setup. And the second figure, figure 3b is the reflection coefficient, which is showing the good matching in the required operating frequency band. The next we will see the power divider to excite the antenna array. So we are using the 8 antenna element over the frustum body. For that, we need a power divider to excite it. So for that application, that 128 Wilkinson power divider has been designed. Wilkinson power divider has a good isolation among the output port, and it will reduce the crosstalk. Also, it works on a wider bandwidth. So the figure 4b and 4c are the reflection and transmission coefficient. From the reflection coefficient, it is visible that all the ports are below -10 dB, and it is giving the good impedance matching. From transmission coefficient, the insertion loss are below the maximum insertion loss we are getting 1.34 dB, and the magnitude wind balance is coming at 0.15 dB. Further, we will see when the power divider is connected with the antenna, then how the result will come out. So the figure 5a is the geometrical view of the power divider with that frustum shape. They both will be connected together as a one body, and this the single body will help it to make it as a lightweight design, because there is no need of keeping anything extra structure to holding antenna or holding power divider individually. And the figure 5b is the reflection coefficient, and the next we will see about the azimuthal, the gain and the radiation pattern in the azimuthal plane. So the design is focusing on the shallow angle of the antenna for 70 degree to 90 degree. The polar plots has been shown from figure 6a to 6d at frequency 4.4 to 5 gigahertz with the step of 0.2 gigahertz, and the ripple and this polar plots is plotted at azimuthal gain plot of 70, 80, 90 degree. The second figure is a 6e, is the figure from between ripple versus the frequency points. And the ripples means the difference between the maximum to minimum in the gain in the azimuthal pattern. and the ripples in the azimuthal omnidirectional patterns are tried to keep below the 5 dB. And next, we will have the alternative approach for high bandwidth, for the high bandwidth, and explain to switch and cover the desired region over 360 azimuth. The azimuth beam will be sufficiently wide to accommodate the platform motion of pitch, roll, and yaw. So if the base station is located at a specific position, the switching topology is proposed for that kind of scenario. So first we will discuss about the power requirement for both active and the passive array. And okay, so we will start with the passive array. So out of 8 elements, if one element have to radiate the 0 dB power, in that scenario, the input power supposed to be 19.53 dB. 19.53 dB, which will include the loss of the power divider. But if we have an active array with the TRM and the switching capability, the TRM with the gain of the TRM is transmit and receive module with the gain of the 20 dB, the requirement of input power will come down to minus 0.44 dB, which is huge. And also generating that 19.53 dB or 90 watt is quite challenging. So next we will talk about that how efficiently we can use this energy. Because if the target at a base station is known, so radiating energy in all direction is not a very good idea. So depending on the coverage demand in a particular direction, we can utilize this array as a directional and the omnidirectional both. So for the given sector is a 45 degree, and for this sector, first we have to find out that what is the number of elements should be excite in a one time. So we have taken 2 element and the 3 element case, and we analyze based on the gain performance over the 45 degree sectoral region. So from the figure 8B and 8C, that is a gain plot between minus 22.5 to 22.5 45 degree sector, and the 8D is the plot of the it's a plot of the gain advantage of 2 element case over the 3 element case. And from all these 3 figures, it is observed that the gain and the ripple are less in the 3 dB case due to the phase difference caused by the conformal structure. So, and 2 element case has more gain covering 45 degree sector and can switch to the adjacent sector whenever the loop angle goes beyond the 45. So next to that, keeping this 2 element, the 8 sector are there, and switching that one set of element to another set of element, the sector can be changed. And that plot has been showing for the 8 switchable sector with 2 element with 80 degree, 90 degree, and 80, 90, 70, 80, 90 degree elevation angle. And it is visible that azimuthal coverage of 360 degree can be achieved with appropriate switching of the 8 sectors, and also powering all the elements can give the omnidirectional radiation pattern. So now I'm concluding that work, the objective and motivation of this work, that design a array antenna for A2G communication system, which can operate at 4.4 to 5 gigahertz. And the work has been the work solved the challenge of the PEC body effect on the radiation pattern of antenna. We have done by using by optimizing the cone angle, and it reduced the ripple in the radiation pattern. Further, the active array architecture has been proposed for the 45 degree sectoral coverage, and this analysis provide the potential of this design for A2G communication system. Thank you.
Okay, very nice presentation. Thank you, Mrs. Masum Fermat. And there is one question in the chat box from Mr. Priyo. What specific applications in the future that could benefit from the proposed custom shape conformal antenna array for the A2GC systems? Please, Mrs. Masum.
Yes, I'm audible.
Yes.
So this design has been done for aircraft communication system only, aircraft to ground communication system. But if you have any scenario where you have to keep the antenna below the PEC surface, in that application, wherever you need that kind of scenario, you can use that. Because that frustum angle has been, optimized based on that PEC body effect. So,
Okay. Is it enough,
Okay,
Mr.
Gwen.
Priyo?
yeah.
I think it's enough. Yes, I got the point.
Yes. Okay. Thank you, Mr. Priyo and Mrs. Masum. Is there any question at all? Still have 2 minutes. Okay, I think there is no any more questions, so I will stop the session. Thank you again, Mrs. Masum Verma, for your presentation. And before we continue to the next presentation from the last presenter, let me start documentation first. So the documentation will start with the co-host. Okay. Co-host, you can start
Okay.
the documentation.
Please open your camera for first page, 1, 2, 3, and then for second page, 1, 2, 3.
Good day, everyone.
Yes, please continue the presentation.
Okay.
Okay, thank you, Ms. Ria. And for the next presenter, we have the last presentation from Mrs. Mrs. Aziz Hussein from Nineveh University, Iraq.
Okay.
Will be deliver a presentation about configuration of hybrid clustered structures in large planar arrays for optimizing beam pattern coverage. So, Dr. Hussein Ibrahim, the time is yours.
Okay. Good day, everyone. My name is Nazik Hussein, and I am one
Thanks
of
a lot, Mr. Chairman and Mr. Co-Chairman. So today
sorry.
I am going to talk to you about the presentation of our paper under title Configuration of Hybrid Cluster Structures in Large Planar Arrays for...
Sorry.
Yeah, sorry. Do you want to present by yourself or by video?
Tamam?
Do you want to present your presentation in yourself or by the video? Because we have a pre-recorded video in here. I think the video is ready to show, so you can wait until the video is ended. Yeah.
Good day, everyone. My name is Nazik Hussein, and I am one of the participate in this researcher. It is an honor to present this paper on behalf of my supervisor, dear Ahmed Jamil. So today I am going to talk to you about the presentation of our paper and the title. And the title Configuration of Hybrid Cluster Structure in Large Planar Array for Optimizing Beam Pattern Coverage. Presenter Nazik Hussein Ibrahim, and other authors, dear Ahmed Jamil, Abdul Qadir, and dear Ja'far Ramadan. I will begin the agenda of our paper. The agenda of our paper contains introduction, the problem formulation, simulation result, and last one in conclusion. Introduction: high performance planar array aperture system have been recently gained a lot of researchers interest where many new technology are development from modern wireless communication applications such as drone, microwave, image modern, satellite communication, radar, millimeter wave communication, and etc. Designing large planar array antenna with the dividing of the quickly reshaping the coverage beam pattern and controlling its characteristic in terms of the weight of amplitude, phase, or both make this system attractive and important. However, the large planar array with the radiating element that are regular arrange and independent exciting such the edge element is equipped with an attenuator, phase shifter, sorry.
Hello, are you still there?
Okay, so several synthesizing techniques have been proposed as a balance between the cost complex and performance, such as telling regular and irregular cluster spares, composition, and optimizing some element located on the edge or boundary of the array. In this paper, any efficiently method for construct clustered planar array based on hybrid structure is proposed to partition the large planar array to achieve the desired coverage beam pattern and preserve is proposed in term peak side loop level and half power beamwidth. The problem formulation. We proposed five different structure to amplitude our idea. The first 2x2 hyperplanar array structure hybrid configuration. In this case, we dividing our channel planar array to 4 main cluster. Each clusters contain different number or same number of radiating antenna element. In this case, we proposed using hybrid structure element. This hybrid structure contain cluster and non-cluster element. The problem formulation on this case is details is shown in this equation. We show the equation for the structure contain 4 types of structure. And the second structure proposed 2x2 hybrid planar array structure hybrid excitation. After we dividing original planar array to 4 different clusters, we use different excitation. For example, in this case we use amplitude excitation, and in this case amplitude excitation and phase excitation, and so on. In this case, we different structure and different excitation structure. In the third idea, 2x2 hybrid planar array structure hybrid excitation. After we dividing the original planar array antenna into 4 main cluster, we dividing each cluster from the 4 cluster. Into other 4 cluster. In this case, the equation array factor for structure can be written in this following. The same idea that we use the first in the second idea can be used in this structure. In this structure contain different cluster sub-array and different non-cluster sub-array. And 4x4 hybrid planar array structure hybrid excitation. Also, we can use hybrid structure for range main cluster. Also, we proposed thinning. Thinning approach. This structure and can be using the equation of the thinning factor of number of cluster thinning structure. We can use this equation. The simulation results is shown in this figure. In all proposed structure, we gain the radiation pattern efficiency, radiation pattern that controlled in respect to the peak site loop level, the main and the main beam. The main beam width. The table. Also, we make a comparison with other paper in terms of table with the grade of implement, type of gradient, number of element, type of algorithm, type of excitation, peak site loop level, and half power beam width, and the last complexity. We show the proposed structure by use. We get peak site loop level. In the case of complement only, the minus 24 and the half power beam width 0.092. Radius completion is matched 13 in all case. Completion 13 in all case. And we radius completion. All proposed case, we get a different value of peak site loop level from the minus 70 and from 2 by 2. The amplitude only minus 24 and phase only the minus 70. Conclusion: any efficiency calculate planar array method with investigate basing on hybrid structure technique. The hybrid structure include 2 approach basing on distribution of excitation with the tailing of irregular cluster or in dividing element for each sub aperture. It is clear from the current the result that the desired coverage bin pattern and be achieved by proposed 2x2 or 4x4 tail of the hybrid structure on the main array aperture. This investigate also demonstrate the source of integrated the thinning technology with hybrid composition with preserving pattern characteristic in term pixel loop level and half power. Moreover, the using of hybrid structure with large power reduce the effect of mutual coupling between sub aperture as well as between the cluster and in dividing element. The simulation results show that the efficiency of the proposed approach in preparing large array from using in modern communication application. Thank you for listening.
Okay, thank you again, Mrs. Nasik Hussein Ibrahim, for your informative presentation. And I invite the audience, if you want to ask something to the presenter, you can raise your hand. Is there any question? Or you can type your question in the chat box. Okay, I think that's no more question anymore. So we will conclude, and I will very thank you for your presentation and your presence, Mrs. Nasik Hussein Ibrahim. And now we can conclude the presentation. And once again, I will thank you to all our presenters for your insightful presentation, and to all audience, I thank you again for your active engagement, and please remember to join us again and in the last keynote talk session in the main room after this afternoon break. Yeah. And enjoy the rest of the event, and we look forward to seeing you in the next session. I'm Yohanes Adiyoga. Thank you for your attention.
Recording stopped.
How can you develop world-changing tech without changing your timeline? The answer is simulation. Physics-based simulation generates insights at every step of product development, allowing your creations to get certified, compliant, and on the market sooner. This means you can build a virtual cruise ship and see how it fares on the open sea. Erect a full-scale virtual twin of a factory and make certain it will be operational in real life. Construct the ideal commercial aircraft and ensure it can withstand the elements. With simulation, no matter what you dream up, it will be enhanced with data, insight, and most of all, revelation. Simulia, reveal the world we live in.
So Simulia is the dedicated simulation brand from Dassault Systems. It enables designers and engineers to physically validate their designs in a virtual environment, and that can accelerate innovation and it can save time and money by reducing physical prototypes. So Simulia covers a wide spectrum of different engineering disciplines, from structures and multi-body systems to fluids, electromagnetics, and vibroacoustics. It's also got powerful automation and optimization technology that underpins all of those disciplines, which really allows analysts to make the best engineering decisions in the development and the validation of their products. The Simulia solutions are available both as standalone desktop applications and within the cloud-based 3D Experience platform. The same underlying technology is used by both, but the 3D Experience platform offers tighter integration of the Simulia solutions and the rest of the Dassault Systems portfolio. So the SOLIDWORKS simulation solutions are actually very good for many different simulation problems. But when you start to simulate more complicated physics, you may find that you hit the limitations of what SOLIDWORKS can do. That's where Simulia comes in. So Simulia has a wide breadth of capability and it can do things which SOLIDWORKS simulation simply can't do. It can also do things which SOLIDWORKS can do, but do it a lot better in terms of accuracy, in terms of speed, and in terms of reliability. Simulia also has a larger R&D resource than what SOLIDWORKS simulation has. So with Simulia, you can be confident that you'll always benefit from the latest advancements in simulation technology. Some of the greatest benefits of 3D Experience Simulia stem from the 3D Experience platform itself and its tight integration with the Dassault Systems portfolio. It allows users to collaborate easily and provides a consistent user experience across the Simulia solutions, irrespective of the type of simulation you're working on. The cloud-based nature of the 3D Experience platform also means that you can run your simulations in the high-performance cloud compute infrastructure, meaning that you can run the most complex simulations on even a basic laptop. Given how much capability there is within the Simulia solutions, there can be quite an awful lot to learn. With that said, there are dedicated training courses for each of the Simulia solutions, and that's available both in a classroom and through an online learning portal. And for every new Simulia user, we'd look to provide a degree of onboarding to help with their successful adoption of the software.
Recording in progress.
There are a few different options available when it comes to licensing for Simulia. Most people will opt for a quarterly or an annual subscription, but it is also possible to access a perpetual license of some of the Simulia solutions. When it comes to cloud compute on the 3D Experience platform, many of the roles include this at no additional cost to some extent, but if you want to fully unlock the power of the cloud, you'll need to purchase additional credits and tokens. The most well-known Simulia solution is probably Abacus, which is the dedicated structural finite element analysis package. But other key solutions include XFlow and PowerFlow, which operate under the fluids domain, CST Studio Suite and Opera under electromagnetics, Wave 6 under vibroacoustics, and SIMPAC under multibody.
Railway System, or LRS, is a subsidiary of PT Land Industry Persero, which has been established since 2012 to fulfill various needs in railway sector, with long experience in railway sector for almost 30 years. LRS becomes a market leader in E&M railway sector in Indonesia, including products, engineering, and services. In a regional market, LRS has been acknowledged as a strategic partner to develop turnkey E&M system and perform multinational partnership in turnkey E&M system field, both for light rail and heavy rail. LRS acquire both national and regional large-scale projects according to its great work and experiences. As to prove our commitment in reaching our vision and mission, LRS products such as SealSafe 4000 and SealTrack LS 3000 has been certified by Ministry of Industry for domestic component level. LRS has been certified by the International Engineering Certification through ERCE, Certified Professional Engineering PII, and Company Certification ISO 9001, ISO 14001, and OHSAS 80001. LRS the most reliable world-class partner for railway system and turnkey light rail E&M system. And our mission is to contribute improving people productivity and mobility through delivering reliable and safe railway system. We are land railway system with innovation, engineering, services, and partnership with delivery safety and capacity.
Hello everyone, now we have completed the 14 paper presentation sessions and I would like to thank all presenter, moderator and participants. We hope that it can aid you in your next research endeavor. Now we have come to the fourth and final keynote talk, which will be delivered by Associate Professor Jiafeng Yao. And this keynote talk will be moderated by Dr. Marlin Ramadan Baidillah. We'll introduce to you the brief profile of Dr. Marlin. He received his Bachelor in Physics from Universitas Indonesia and Master degree in Civil and Structural Engineering from National University of Malaysia. He received his PhD degree in Mechanical Engineering from the Division of Artificial System of Science, Chiba University, Chiba, Japan in 2018. He has been a research fellow with the Multi-Phase Flow and Visualization Laboratory at the Graduate School of Science and Engineering, Chiba University. Since 2018, under the GSPS Postdoctoral Fellowship and the Chiba University Fellowship. Previously, he has been as a research coordinator at CTech Labs Edward Technology in Tangerang, Indonesia from 2012 to 2015. He has been with the National Research and Innovation Agency, or BRIN, in Indonesia since 2022. His research interests include sensing, imaging, and tomography systems for biomedical and industrial applications. Please welcome Dr. Marlin Ramadan Baidillah and Associate Professor Jiafeng Yao.
Okay, thank you, Ms. Ardita, for the introduction of this session. Welcome back, everyone. It's very wonderful that we are arriving at the last session of our conference. And at the moment, we will have a keynote speech from China. And hello, Yao Sensei, are you present? Oh, here you are.
Yeah,
Okay,
I can hear you.
Yeah. Okay, so I will introduce Professor Yao to you about his curriculum vitae before. Host, can you go to the slide? Okay. So Professor Yao is graduated from China in 2008 for bachelor degree, and then going to 2011 for the master degree in China as well. And then he got PhD degree in Japan in 2014. And within 2014 and 2016, he has been a research fellow in Chiba University, Chiba, Japan. That is the time we meet each other. And currently, he is associate professor in mechanical and electrical engineering, Nanjing University of Aeronautic and Astronautics, China. So today, Professor Yao will talk about electrical impedance tomography and its application in medical field. And I believe that it's not only for the medical, I think, so it's also could be applied in non-medical, such as industrial process. So it's it's my pleasure to invite you, and then thank you very much to come to our conference. So I believe that perhaps the introduction of this technology to everyone, particularly in Indonesia and my company, can open mind new challenge and then new collaboration perhaps in the future about the development of this application, not only in the medical field, but also in the industrial field as well. So welcome, Professor Yao. If you are ready, I think time is yours. Can you start? Okay, great. Okay, time's yours.
Yeah,
I think the slides will be swift. Okay, that's great.
This screen.
Okay, good.
Thank you, Dr. Malin. Long time no see. So I also graduated from Chiba University. So today's topic is the electrical impedance tomography and its medical applications. I established an intelligent biomedical engineering measurement lab. So today I will introduce the work in my lab. It includes background hardware development and the three applications: cell measurement, tumor measurement, and lung imaging. So firstly, I will introduce the background of our research. As we all know, for the medical imaging research area and applications, we know that before the 1990s, we focused on the physical imaging. That means the X-ray, B-mode ultrasonography, DR, and after that, it's that means before the COVID-19, we call it the digital imaging. So where you can see very popular, the MRI, CT, and PET-CT is very, very popular. But why I separate this period after COVID-19? Because after COVID-19, especially in China, we must focus on the medical detection at the early stage detection. That means the functional imaging. For the function imaging method, there are several methods: acoustic, electromagnetic, metabolic, molecular imaging, several methods. During this method, our method is the one of this function imaging method. We call it the electrical tomography method. For this method, Dr. Malin is very familiar with this because we graduated from the same lab in Chiba University. This is our supervisor. Very long years ago, last 1990s, they developed the first electrical tomography device we call the electrical capacitance tomography in Manchester. After that, this method developed, this technology developed to several applications, including the chemical engineering, and then developed in Chiba University. Half of the tomography method applied in the medical or biomedical applications. This is we detect the muscles in this area. But in recent years, one of the EIT, we call the EIT, electrical impedance method. This tomography method has been commercialized for the brain detect. After that, now in China is more and more popular. We use is the lung imaging method. The company name is Dragon. So for this method, we call it developed from industrial to medical applications. Even in recent years, the medical applications is a hot topic. And also new bio applications appeared. For example, in our lab, we applied several new applications and more commercialized products. But in China, till now, only one commercialized product is the lung imaging tomography method. So I will introduce the principle, because our research use the electrical impedance tomography method. So we simplify as EIT. It's one of the tomography methods. It uses the impedance. Impedance includes the capacitance and resistance, so combined together. So the principle is like this. We inject one pair of current and we capture other pairs of the voltage. And then we use some calculations to resolve the inverse problem. That means we get the voltage around the object, and then we calculate the conductivity distribution in this area. For example, this banana and a cucumber. The banana's conductivity is different from the cucumber. So if we get the conductivity distribution in this area, we can use different colors represent the conductivity distribution. So we can find the blue area is the image of the object. So this is a simple principle. That means the process is inject current, capture the voltage, and then reconstruct the conductivity distribution. So in our lab, we applied this technology to several applications. For example, the brain detects the stomach, lung, bladder, and muscle. Several applications have been developed. But in today's topic, firstly, I will introduce one of the applications. Also, is a very hot topic. Now, in China, we developed the microfluidic sensors for the cell measurement. So the second section is I will introduce the hardware we developed. So we use the repeater and multiplexer, and also we call the voltage control and some hardware to combine together to develop this hardware. So this repeater generate the voltages, and we use the VCCS to convert the voltage to current, and then use the multiplex to switch the current injection. And finally, we capture the signals around the object. So and also we developed software to reconstruct the images. So this is a laboratory, several products we developed. After that, I will introduce the cell measurement. For the first applications, I will propose a new concept. As we know the multi-phase flow. For the multi-phase flow, we call the solid, liquid, and gas. But we know inside a cell there are some we call the specific molecular to aggregate, and subsequently from a specific reaction zoo in the complex intracellular environment, we call the membraneless organisms. That means there's one of the we call the protein can be appeared as this membraneless organism. So we can see we can use liquid phase. This is also two-phase, liquid. For example, is oil and water. The viscosity is different, so it can if the oil is little, it can aggregate it as a droplet. So this is a liquid phase separation to show the principle of the membraneless organelles. So after that, I give you a more simple understanding example. The liquid phase separation, we call LLPS, associated with many existing incurable diseases such as Alzheimer's disease, Parkinson's disease, cancer, at all. So that means if the process of the protein cannot generate it, it will this LLPS process will be disordered, and then it will generate incurable diseases. So how to monitor the process of the LLPS is our object. So for this purpose, we developed the microfluidic sensors. Why we can get this process of cells? We established and we call the equivalent circuit model for cells liquid phase separation. That means for a single cell, the membrane behaves like a capacitor, and the proteins behaves like a resistor. And then we come down this is a double layer, and this is the electrode. So we establish an equivalent circuit model. Then we can get the signals, voltage signals, after we generated a series of electric current. So this is a reason why we can detect a single cells. This is our experimental setup. We use a injection pump and then inject the cells into this fluidic sensor, and we use a impedance analyzer to analyze the signals. So in order to get LLPS models, we also used this microfluidic devices to generate. This is the fountain of the LLPS. So this is the oil, around is the water. We want to monitor the generation process of the droplet. So this is we also studied the simulation of the phase separation process. So this is a model. We also use some equations and free energy diffusion equation, free energy functional, and classical CH equation So this is the time we inject oil in the water after increasing the voltage, the volume of the oil, we can get a process of the phase separation. So this is the simulation method, and then this is the experimental results. We developed a EIT sensor on a PCB board with 16 electrodes, and this is the oil and water mixture. This is the image reconstructed by EIT using our hardware and our algorithms. So this is the phantom. This is the EIT result. Yeah, this is the experiment results. Next step, we want to use the real cell to monitor this process. For example, in our experiment, in our lab, we have bought this setup and also developed a very small microfluid device because the cell is very, very small. So the electrode we use 8 electrodes. So we also get a EIT image. We detect the single cell in this microfluidic. As we know, from the research papers, we know in the research papers, the smallest cell can be detected has been published from Edinburgh University. University of Edinburgh is 1 millimeter. So we decreased the accuracy of the EIT. Firstly, we developed this device and a fluidic sensor. We can detect a cell diameter is only 20 micrometers. So we think it's very, very small. So this is also very difficult. So this is the first application. Next application is for the tumor measurement. We also, we can call it, this is a planar EIT. Traditional, the EIT is around the object. So in order to detect the cancer boundary, we develop a planar EIT. So we can see in this area we use the 16 electrodes, and when you it's very similar, like it's like a stamp. We stamp this sensor to our tongue. The tongue tumor can be detected. So this application has been used in Nanjing Medical University in the hospital. And next step for the cancers, we also detect several types of the cancers. For example, these 3 types. We found that for the tumors, this is a tumor. For the tumors, the impedance is a little higher than other tissues. So this is our results. And also here is some abnormal. We can find the abnormal area, and we found the boundary of the cancer. And another very interesting application is we have used the EIT for we call endoscope EIT. Yeah, we can combine EIT sensors to the endoscope, so we can detect the tumors inside our body. For example, this is the stomach. And also we combine this method to the soft robotics. We use soft robotics to inject, send the sensors to the positions inside the body. So this is another application for the tumors. The final application is for the lung imaging. For lung imaging, we also develop the EIT method. So we can use the one belt around the lung, around our chest. We use the 16 electrodes. When we breathe, we can find this area, the blue and white area. that means this area is the breathe is very well, so the lung is well. If there are some problems, this blue color will be disappeared, and also other indicators we can use. So for this hardware and software, we have commercialized this machine, and also we have applied in the hospital. Later, I will show the examples. And based on the previous image is the 2D EIT. Also, we have developed a 3D EIT. So this is our originality. We only use one bell to generate 3D images. As we know, for the 3D images, we should calculate many data. So it will be slowly. It will be very slow for the process. But for our algorithm, we have developed a real-time 3D EIT. This is the first time we developed. So for the 3D, we can see the whole lung images here. So we have applied this method to detect some problems in hospital. I will give several examples. The first example is for the lung problem. So we can see for this person, his lung has some problem. He cannot breathe in this area. We call this is the left. This is the left lung. This is the right lung. So this direction, we see this view. From this view is same with the CT image. So this is the left lung. In top left lung, there are some problems. He cannot breathe. So from this monitor of the process, it can help the doctors to use the medicines or some method. This is the first application. For the next application is we call there's a very general problem in China. We call the chronic obstructive pulmonary disease. So in order to monitor this problem, the method in hospital, now the method in hospital is a pulmonary function. Our method AIT, the doctors will be, it's difficult to detect this breath curves because it needs a person to blow this device. Many patients cannot blow. They don't have any energy to blow. So for our device, we developed the EID device. We can detect the lung imaging directly. Don't need the patient to blow. So this is very easier to use, and also we increase the accuracy. So we also compared with our method and with the report in the hospital. This is a pulmonary function used in hospital. This is our device. We get the results error is 5.19. And the last application is for the newborn baby. This is very interesting. Also, we detect this result is the first time in China. For example, this we know the newborn baby, it cannot breathe by using the diaphragm. So the baby will, this function, this diaphragm. For our adults, we can use this function. But for the newborn baby, in this function is not very good. And in the baby's lung, during the lung is some waters. So when the baby born, he likes cry. Why he cries? Because when he cries, he can breathe. He uses the chest to breathe. So in this process, during this process, there are many problems, but the doctors cannot know the real conditions inside the lung. There's no good method because the the CT has a radiation, but we developed the EIT method, no radiation. So it's a very good method. We firstly applied this method and this device in Changzhou Hospital near Nanjing. So this is the first result in China. So also we applied in many, you have used many clinical applications in hospital, also very many famous hospitals in China. The first is for the COPD. This is for lung breathing. This is for the newborn baby. Yeah, this is in Beijing Chaoyang Beijing Chaoyang Hospital. Has many applications. So for the last applications of the lung imaging, we have commercialized this device. Also, we have got the certificate of medical device registration in China. That means if we get the certificate, we can sell this device to the hospitals. So also this device has many advantages compared to the device from Germany. So this is a medical device innovation approval. This is the first device developed by our lab, and also is the first device in domestic. Yeah. Anyway, I will give a introduction of our team. In our team, we have several members, especially for Bosun, Chen Ye. We are very familiar. We are from the same lab, like Dr. Mali. Maybe Dr. Mali knows them very well. And also we have a doctor named Yang Wu. He just graduated as a PhD student from our lab. Now he working in another university, also in Nanjing. So this is a group of members. And also we have more than 30 master students and 3 PhD students. So now our lab, we developed more and more devices and also commercialized devices. Also, I want to invite, if anyone interested in our device, I will send some introductions to you. And also during this year, we also established a joint lab with University Gajah Mada in Indonesia. From this year, we also established more and more collaborative researches. We also signed the MOA, MOU, and many more and more collaborations has been developed. Our students always go to Indonesia, maybe 1 year, 3 or 4 times. Also, we have developed the PhD joint programs. Anyway, we have many collaborations with Indonesia. If some professors or doctors are interested in our research, please contact me or contact Dr. Mali. And as a conclusion, I will conclude my topic. We have developed the EIT, and this EIT becomes a very hot topic after COVID-19. Before this, it's seldom. So now it's a very hot topic in China. And also our laboratory has developed EIT hardware, software, and algorithms of all the technology relating to the EIT we have developed. And also we have a series of frontier applications. And also the prototype of EIT for lung imaging in our lab has been commercialized. Anyway, thank you very much for your listening. Thank you.
Thank you so much, Professor Yao. It's very interesting and wonderful presentation. And I'm quite amazed that the research is very fantastic. It's very fast. That I remember that last time you try to commercialize it, right? But currently it's already commercialized, right? So
Yeah,
it's already proven. So I believe that there are so many questions, not only for me. I have a lot of questions for that, but let me ask for the audience, the presenter, the participants here. We already have 2 questions in the chat box. So the first one is from Mr. Effendi. According to your hardware controller, you use the Raspberry. What is your consideration? Why not use another controller or processor such as FPGA? Do you mind to answer directly or?
Yeah.
Okay.
Oh, I will check the questions. Hardware controller use Raspberry. Yeah, Raspberry. What is yeah? This is actually the FPGA. I think the FPGA is better. Why we don't use FPGA? That means at the very early stage, I think the Raspberry now we use is more stable or more convenient for us. But it's very expensive. Now we have developed the FPGA instead of Raspberry, because if I said frankly speaking, and firstly, in our lab, we don't have high technology to develop FPGA, but no, we have developed. So we will use FPGA instead of Raspberry step by step. For the next products, we will use FPGA. So we just finished FPGA.
I see.
Yeah, that's my question. Yeah.
That similar condition, I think, in like in Indonesia, that several laboratory, whenever they try to develop a prototype before the commercialized one, instead of making from the scratch, they try to, put some model together and then make a whole one systems as the perfect one. But later, after they know each other about the knowledge, then they make another one by one from the scratch. Okay, thank you for the question and the answer. And we move to another question. This is from Dr. Iman Firmansyah. He's asking about the real-time 3D EIT experiment. How many sensors usually use?
Yeah, in the real 3D experiment, we use the 16. Only one belt includes 16. But for actually, if we want to get very accurate 3D images, traditionally we always use 48. That means 3 layers sensors, 3 layers of sensors. But for the real application, it's difficult, or the patients don't like so many electrodes. So only we use the 16 electrode. But for 16 electrodes, the accuracy is low. To solve this problem, we developed very new algorithms. We use one belt, one layer of including 16 electrodes to generate 3D electric field. And then finally we can calculate the 3D image. But for this 3D image, we also use the AI method. We use a machine learning method. That means we also capture the 10,000 city images to help to reconstruct our 3D image. So my answer is in 3D, in the real application, we use the 16. But for the experiment in the lab, to study the algorithm, we use the 48. This is my answer.
I see. So, okay, following to these slides, I'm quite interested with the cardiac effect during the measurement. Usually the impedance source from the cardiac is quite significantly affect the impedance from the lung. Did you consider from the system about cardiac?
Cardiac, yeah. You mean actually the cardiac also influence the image, but we use time difference. we use a time difference method to calculate the image. That means, and also we use we select proper frequencies. So for the first, the time difference, we calculate because the difference of the long breath is much larger than other signals. So finally, we only get the image of the long breath, so this image. For the second method, we use first the time difference, and then we for the real calculate, and also we know actually we first we know the position of a cardiac, so we in the image reconstruction we also we decrease the signal, these errors signals.
Okay.
Yeah.
So what
In
frequency
the-
did you use for the measurement?
process. Mm.
In the measurement, what frequency did you use? Is it 100 kilohertz?
Yeah, we use 50 kilo.
50 kilohertz.
50 kilo. Yeah.
Yeah, it's quite standard for the body measurement. Okay, I would like to go to the participants. Is there any other person want to ask directly to Professor Yao? So, okay, Professor Yao, once more. I'm quite interested with the cell measurements. You use the for application LLPS. So usually whenever we start the analysis, one thing that we should consider deeply is about the calibrations, right? So the impedance reference itself should be very accurately. Otherwise, we cannot eliminate the effect from the contact impedance, from the electrode, the different electrode dimension, and so on and so on. So do you mind to explain a little bit about what kind of calibration condition did you use for this system application?
Yeah, actually, for this problem, when Dr. Mali and I in Chiba University, we also discussed. At that time, we have found many problems. It's difficult to measure the cells because the cell is very, very small. And around the electrode, it also generates a double layer. So this is very difficult. So in our experiment, we calculate and calculate and measurement. Finally, we get a single cells EIT image. We have some new method. Firstly, we established this equivalent circuit model. That means we generate a frequency we use a spectroscopy method, generate the frequency, and we have we fit this spectroscopy, and then we calculate each parameters of the component, and then we can decrease the influence of this component. This is the first one. And then next point is we use many like a Faraday cage or something to decrease the noise around this area. Finally, for the microfluidic sensors, we also use many other, we use such as the cables or in the PCB, or we also use some method to avoid the influence of the noise. So this is our method. Yeah, it's actually it's very, very difficult. So we need to improve the accuracy from the algorithm, hardware, and software. We all need to improve.
Yeah.
Yeah, this is
It's wonderful. Just for these slides, I got many research topics. Yeah. Okay. Yeah, so many questions, but unfortunately, okay, we got new one. This is from, I think we still have time. This is from Mr. Priyo. for the viscosity measurement of the blood using microfluidic, what do you use to build this microfluidic 3D print or CNC, which of course create two parts, at least to combine? And how do you combine it but avoiding leakage and not affecting measurement parameter? So
okay, I will check the viscosity measurement of the blood.
He's wondering about how to manufacture the sensor.
Of course, to create the two parts, at least to combine leakage, not affecting the measurement. Yeah, I'm not familiar with for the viscosity. For the blood, yes, the blood measurement, we studied the blood flow several years ago. At that time, we detect the thrombus detection. At that time, I think for the calculation, the data processing, we use the time difference. That means we detect the signal, and then we inject the blood. Finally, we use the difference. We calculate the difference. So other method, I'm not sure. Sorry.
Yeah, I see. So many options for that. So later, if Mr. Priyo, if you still wondering so many questions, you can ask directly to Professor Yao. And ladies and gentlemen, we are very sorry that because the time is very limited, we could not go further for the next questions. And at the end of this session, I would like to conclude that Professor Yao, with his research team in China and also in another country with the same research field as well, we are trying to develop non-invasive, right? Non-invasive and non-intrusive tomography system that particularly, mainly, hopefully, that we are going to make an alternative based from the conventional one like X-ray or MRI that really bulky for the emergency situation and also for the portable situation. So currently his research in his laboratory try to develop starting from the hardware and then go to the software, and currently it's already commercialized for several applications such as lung imaging and for the cell imaging applications. So I believe that some of you may be quite interesting. So Dr. Yao already mentioned that whenever you want to contact him, you can contact him directly, or maybe you can ask to me, and then we can go further for the next communication. Professor Yao, thank you so much for your presentation in this keynote speech, and we have a token appreciation to you in recognition for the delivery of keynote talk in this conference, International Conference on Radar, Antenna, Microwave, Electronics, and Telecommunications, that organized by BRIN and also Rahaya Mulya and other sponsors in these slides. Thank you so much. See you again next time.
Thank you,
I think,
yeah,
I think, ladies and gentlemen, that is what we can provide to you, and that is I can guide for this keynote speech. And later, I would like to give the screen to the MC again. Thank you so much.
Thanks to Professor Jiafeng Yao and Dr. Malin Ramadan Baidillah for having delivered our final keynote talk session. Now that we have completed all talks and presentation, I would like to invite you again on another round of screen capturing. Okay, please turn your camera on. So we will do it like in the usual 3 times. And for the first screen capturing, please be ready in 5 seconds. Okay. For the first screen capture, in 3, 2, 1. Okay, and for the second, in 3, 2, 1. And last, in 3, 2, 1. Okay, now moving forward, Dr. Wilman Septina from our Technical Program Committee will announce the awards of ICRAMED 2024. Please welcome Dr. Wilman Septina.
Thank you, MC. So I'm Wilman Septina on the behalf of the Technical Committee of ICRAMED 2024. So I would like to announce 2 awards. So let's wait for the slide to show. Okay, so first award is the Best Paper Award. So we have received 69 accepted papers this year, and after evaluation of the quality of the paper, so the best paper. Next slide, please. Yeah, the best this year goes to Mr. Mustafa Kuchuk from Istanbul Technical University and Aselsan AS, Turkey, for the paper entitled Novel Square Wave Jamming Strategy for Countering Sequential Lobbying Radars. So congratulations, Mr. Mustafa. Let's give virtual applause to Mr. Mustafa. And the next one, we have the Best Presenter Award. So this year goes to, next slide, please, Mr. Shahrukh Hamidi from University of Waterloo, Canada, for the paper entitled Multispectral Based Imaging with Application to Millimeter Wave Imaging at W band. So congratulations, Mr. Shahrukh. Let's give virtual applause to Mr. Shahrukh as well. So winner of the awards will receive 50% discount for the registration fee for the next year's ICRAMED 2025. So please be sure, Mr. Mustafa and Mr. Shahrukh, to join our ICRAMED next year as well. So the committee will contact you for the award certificate and also the details of the prize. So congratulations once again to the winners of the Best Paper Award and also Best Presenter Awards. So I will return now to MC.
Okay, congratulations for all the winners, and also thank you to Dr. Wilman and our TPC program for having brought to us the award commencement. Now I would like to invite Dr. Pauline Octaviani as the chair of ICRAMED 2024 to officially conclude the 2024 International Conference on Radar, Antenna, Microwave, Electronics, and Telecommunications. Please welcome Dr. Pauline Octaviani.
Good afternoon, our distinguished keynote speaker, patron, invited guests, presenter, and all participants. First, I would like to extend warm congratulations to the winner of the Best Paper and Best Presenter Award. Now we have arrived at the closing of the 13th International Conference on Radar, Antenna, Microwave, Electronic, and Telecommunication 2024. Over the past 2 days, we have witnessed an exceptional exchange of ideas, groundbreaking research, and collaborative dialogue. We have enjoyed inspiring presentation, in-depth discussion, and valuable networking that showcase the global commitment in advancing technologies in radar, antenna, microwave electronic, and telecommunication. On this occasion, I would like to express our sincere gratitude to everyone who contribute to the success of this event. First and foremost, our heartfelt thanks to the IEEE Indonesian section for their invaluable support as our technical sponsor, as well as to the Agreement Advisory Board, the Chair of National Research of Innovation Agency, Professor Laksana Trihandoko, and then the Head of Research Organization of Electronic and Informatic, Dr. Budi Prawara. We are also deeply grateful to our sponsor, PT Nusantara Sekom Infotech, PT Radar Telekomunikasi Indonesia, PT Mars Sistem Integrasi, PT Yong Dinamis Indonesia, PT WAP Andalan Indonesia, PT Serviam Abadi Murni, Bank Rakyat Indonesia, and PT Land Railway System, whose contribution has been essential to this event success. Our deep appreciation extends to our distinguished keynote speaker, patron, dedicated reviewer, session chair, authors, and presenter. I would also like to thank the organizing committee who have worked tirelessly and with great dedication to make this conference possible. We sincerely apologize for any shortcoming that may have occurred during the conference. Now, I officially declare this conference closed, which say Alhamdulillah, all praise to Allah, the Almighty. We look forward to welcoming you all again at ICRIMET 2025. Together, we will continue pushing the boundaries of innovation. Thank you all for your participation. See you next year.
Okay, presenter, participants, and distinguished guests, now that we have reached the end of ICRIMET 2024, I would like to thank all of you again for your participations and also enthusiasm of this conference. I hope the talks and discussion we had in these 2 days will be beneficial in your future work. So, hope we can meet you again at the ICRIMET 2025. See you.